Before we cross to interstellar space, we must understand the shore. I like to begin where the light thins and the wind goes quiet. At the skin of our little world, within a world the sun's vast bubble that carries us through the galaxy. Imagine the night sky not as an emptiness but as an ocean, and our star as a ship that has been sailing for billions of years, leaving in its wake a shimmering wake of particles and magnetic fields. That wake inflates a protective cocoon around every planet, moon, grain of dust and radio call we've ever sent. We call it the heliosphere, and it is the difference between a sky that is merely dark and a sky that is lethal. The heliosphere is why the word home can sensibly include the space between worlds. It is our shore. In late September of 2025, a new cartographer set out to trace that shore. NASA's Interstellar Mapping and Acceleration Probe IMAP rose from Florida and took its place near the Sun-Earth First Lagrange point, a million miles sunward, where it can face the gale and quietly count what the wind brings. IMAP is built to turn invisible traffic into maps, energetic neutral atoms, dust, electrons and ions, the magnetic field's subtle contortions, all rendered into a picture of the sun's bubble and the space beyond. Think of it as a weather station for the edge of home, placed just far enough upstream to give us warning, and just sensitive enough to show us structure we could not previously see. You might ask why we need a new map at all when two elder emissaries have already stepped off the continental shelf. Voyager 1 crossed the heliopause, the boundary between solar wind and interstellar medium, in late August 2012, and Voyager 2 followed in early November 2018. They did not burst through a wall, they drifted through a change in the music. The instruments heard galactic cosmic rays rise and heliospheric particles fall, and the plasma beyond rang at a different density. It was as if the ocean's swell suddenly shifted beneath the keel. These were the first human objects to taste interstellar seas. But voyages are lines through a landscape. IMAP is a lens. Its trick is simple and beautiful. Far away at the borders of the heliosphere, fast-charged ions born in the solar wind steal electrons from neutral atoms wandering in from interstellar space. In that instant, a charged particle becomes neutral, an energetic neutral atom, and freed from magnetic fields, it flies off in a straight line. Some of those neutrals arrive at our detectors near Earth. If you record enough of them from enough directions and energies, you can reconstruct a ghostly image of the boundary itself. It is astronomy by particles rather than light cartography by messenger. We know this works because we have done it before imperfectly and were surprised. NASA's Interstellar Boundary Explorer IBEX collected such particles and drew an all-sky map more than a decade ago. It revealed a bright, narrow arc, the ribbon, hanging across the sky like a signpost painted by the local interstellar magnetic field. The ribbon was not predicted. It told us that the sun's bubble is shaped not only by the wind we blow, but by the magnetic pressure of the space we sail through. It is difficult to overstate the poetry of that our boundary carries the fingerprint of the galaxy outside, and the surprises did not stop at the ribbon. For years, popular diagrams showed a sharp comet-like bow shock ahead of the heliosphere, a cosmic surf line where interstellar flow would break. Then IBEX and the Voyagers together suggested that the sun is moving too gently and the interstellar magnetic field is too strong for a true shock. What forms instead is more like a bow wave, a softer pile-up without a violent break. The edge of home, it seems, is not a cliff, but a pressure ridge. IMAP will refine this picture, a living coastline that swells and shrinks with the solar cycle. Even the shape of the bubble itself is in lively dispute, which is exactly where you want science to be. The old sketch, a long-tailed comet streaming behind the sun, is not the only candidate. In recent years, sophisticated models have argued for a more compact, deflated croissant, sculpted by magnetic tension into twin jets that fold back into a stubby tail. The truth may be somewhere between the beach ball and the pastry. IMAP's energetic neutral atom cameras, working alongside the lessons from the Voyagers, are designed to discriminate between these possibilities by watching how the boundary brightens and dims across energies and seasons. Why does any of this matter to us here, under an ordinary sky? Because life depends upon the quiet. The heliosphere is a shield against galactic cosmic rays, charged particles, accelerated by distant cataclysms. When the sun's magnetic field waxes and the solar wind strengthens, the shield thickens and fewer of those particles reach the inner system. When the sun's activity wanes, the gate opens a little wider. Our bubble modulates the radiation climate of the planets and the safety of our astronauts. It is not fanciful to say that habitability is in part a magnetic and meteorological story, and that IMAP's maps will help us read it. What I love most is that this is at heart a human story about perspective. A pair of elderly probes feel the cold rain beyond the gate. A new observatory at the Lagrange point paints the gate itself. And somewhere between their data and our imagination, the idea of home expands. We will watch over years as the ribbon breathes, as the sun's long exhalation swells and subsides, and as the line between inside and outside shifts by billions of miles. And we will learn perhaps that our shore is more delicate and dynamic than any of our earlier drawings suggested. So let us set out properly. In the next part, I will walk with you from the sun, outward step by measured step, through the hot corona, and into the solar wind, past the termination shock, and across the heliosheath, until together we reach that faint, wavering frontier. Listen for the first hints of interstellar weather on the other side. From the sun outward, then slowly, as if we were walking a shoreline at first light. Close in, the star is not a disk, but a turbulence of light and magnetism. Its outer atmosphere, the corona, is a rare hot veil that blurs the old boundary between star and space. We used to imagine the void beginning just beyond the brightness. Then a daring little craft skimmed the flames and told us otherwise. The Parker solar probe flew into the corona and tasted the magnetic sea from which the solar wind is born, finding that the edge of the sun's atmosphere is corrugated and lively, pocked with switchbacks and folds that flick the wind into motion. To touch a star and bring back a weather report is a line from science fiction written into the ledger of fact. Beyond the corona, the wind organizes itself. It is not a steady breath, but a symphony with slow movements and sudden flares. There is the languid, slow solar wind that seeps from streamer belts, and the fast flows that howl out of coronal holes, both braided by the sun's rotating magnetic field. Taken together, this stream fills a sphere that is not a sphere at all. It is a living river that thickens and thins with the rhythm of the 11-year cycle. Particles and fields leave the sun's supersonic, then sweep outward past worlds and comets and dusty rings, until far away they run into the oncoming interstellar air and must yield. Along that path, the wind threads our space with structure, a spiral of magnetism, gusts and lulls, and the crackle of shock fronts from eruptions, which is why a spacecraft near Earth can feel the pangs of storms that began days earlier on a distant patch of solar surface. Parker's intimations of origin give that weather a face. The wind is not an abstraction, but the continuing touch of the star. Carry on, and the music changes. At some great remove, the sun's gale can no longer outrun the pressure of the medium between the stars. There the wind slows from supersonic to subsonic, an invisible surfline we call the termination shock. Voyager 1 met that boundary late in the year 2004 at around 94 astronomical units. Voyager 2 followed in mid-2007, roughly 10 astronomical units, closer because the sun's breath and the interstellar weather were different then. Between that shock and the next great frontier lies the heliosheath, a warm, turbulent buffer where the solar wind is slowed, compressed, and deflected. It is a place of pressure, negotiations of charged particles being accelerated and reshaped, a kinetic hinterland that swallows shocks and exhales waves. Step by patient, step through the sheath, and you encounter the heliopause, the contact between inside and outside. Voyager 1 crossed that wavering frontier in late August 2012 at about 121 astronomical units from the Sun. Voyager 2 followed in early November 2018 at about 119 astronomical units, and in the quiet beyond, both heard the ringing density of the interstellar plasma. The position of that boundary is not fixed. It breathes with the cycle, with the temper of our star, and with the weather of the local cloud through which we sail. So the distances you hear, 121 here, 119 there, are not cartographers' certainties, but snapshots taken as the tide went out and in. Look upstream and you might expect a crashing bow shock before the sun's prow. For years, sketches showed just that, a cometary helm ploughing a foaming wave. But the measurements whispered a subtler truth. The local interstellar flow is relatively gentle, and the magnetic field beyond our bubble is firm enough that instead of a sharp shock, there is more likely a broad bow wave, a soft banking of the medium, a pressure ridge rather than a breaker. The edge of home, in other words, does not smash the galaxy aside, it negotiates. That is a more beautiful picture to me, and a better one. And what of the bubble's shape itself? The old comet's tail is giving way to stranger pastry. Models that honour magnetism as much as gas dynamics suggest a compact, deflated croissant with twin jets that fold back the field lines, pulling at the wind like a potter's hands on clay. There may still be a tail or tails, but their form is stubbier, more braided, less like a streamer, and more like a pair of plumes bent by the interstellar breeze. The truth is likely a compromise, a topology that shifts with the cycle and the neighborhood, but the theme is consistent. Magnetic tension sculpts the heliosphere as much as simple wind. The next generation of maps will not be pictures of gas alone. They will be portraits of force. How do we see any of this from our vantage near Earth, 100 times closer to the Sun than those frontiers? We cheat elegantly. At the boundaries, fast ions from the solar wind steal electrons from neutral atoms drifting in from interstellar space. In that theft, a charged particle becomes an energetic neutral atom, no longer bound to magnetic fields, free to fly straight toward us. Catch enough of these messengers sorted by their energy and arrival direction, and you can reconstruct a ghost image of the faraway frontier. This was the trick of the Interstellar Boundary Explorer, which drew an all-sky map and found a luminous ribbon hanging across the heavens, a signpost of the local interstellar magnetic field's grip on our bubble. Interstellar Mapping and Acceleration Probe, newly arrived at the Sun-Earth. First Lagrange point is the refined instrument, 3 energetic neutral atom cameras spanning low, high, and ultra energies, a magnetometer, telescopes for ions and electrons, a dust counter, and a suite built to turn particle rain into weather charts of the edge of home. There is a practical tenderness to this. The heliosphere is not only lovely, it is a shield. Galactic cosmic rays, charged remnants of ancient cataclysms, are modulated by our bubble. When the sun is active and the wind is muscular, fewer of those high-energy messengers reach the inner worlds. When our star is quiescent, the gate opens a little and the flux rises. For life on planets, for astronauts in deep space, for the fragile chemistry of atmospheres, this modulation matters. To understand habitability is to understand the magnetic and meteorological architecture of home, and to appreciate that other stars carry their own bubbles, astrospheres that may shelter their worlds differently. IMAP's measurements, Parker's close-in revelations, and the Voyager's soundings beyond the gate braid into a single story, how a star builds a refuge. And there is one more layer of wonder. The ribbon discovered by IBEX suggests that our boundary is not simply pushed from within, but traced and tightened by the field outside, like a shoreline shaped by distant tides. Fresh models keep arriving, not yet unanimous, but increasingly deft, weaving energetic neutral atoms, plasma waves, and magnetic maps into a coherent atlas. Interstellar Mapping and Acceleration Probe will test those atlases against reality, frame by frame, season by season, so that in time we may say not only where the shore lies, but why it curls just so. For now, keep walking with me. We have reached the door where the solar wind yields to the medium between the stars. Next, let us open it a little wider and follow a single particle born near the sun, transformed at the border back along its straight path to our detectors, to see how a map of the unseen is drawn out of pinpricks of arrival and the patience of years. We left a single messenger mid-flight, so let's catch it. Imagine a hydrogen ion born in a fast stream from a coronal hole curling along the sun's spiraled magnetic field. Far downstream, near the wrinkled contact with the space between stars, it encounters a drifting neutral atom and steals an electron. In that instant, it ceases to care about magnetic fields. What was a charged ion becomes an energetic neutral atom and flies straight like a tiny invisible photon with mass. Some of those neutrals happen to be aimed exactly at our instruments near the Sun-Earth first Lagrange point. Count enough of them arriving from many directions and energies, and you can turn particle rain into an image of the far frontier. It is astronomy without light, a map made of trajectories. Now the magic is in the sorting. A neutral atom arriving with a few tenths of a kilo electron volt carries a different story and a different travel time than one arriving with tens of kilo electron volts. The Interstellar Mapping and Acceleration Probe, newly on station at the first Lagrange point, spreads these messengers across dedicated cameras and detectors IMAP low. At the lowest energies, IMAP high, in the middle, and IMAP ultra. At the highest, each tuned to a different slice of the sky and a different part of the physics. Together they let us separate whispers from shouts. IMAP high alone spans roughly 0.4 to about 15 kilo electron volts, while IMAP ultra extends the view into the tens of kilo electron volt regime, and IMAP low reaches down to the faint cool neutrals and interstellar atoms drifting through. Add to that a magnetometer-charged particle telescopes and a Lyman alpha photometer called GLOWS that reads the helioglow in far ultraviolet, and you have a machine designed to turn the edge of home into weather charts. Because these are single pixel images, exquisitely sensitive counters rather than cameras in the usual sense, The map builds up over weeks and months as the spacecraft rotates and scans different look directions. In the same way a lighthouse turns darkness into a sweeping geometry of light, a spinning detector turns point counts into a sky. Change the energy bin, and you change the depth of field. Higher energy neutrals tend to come from slightly different regions and respond differently to the pressures and fields at the boundary. Over time, those layers combine into a three-dimensional portrait of the heliosphere's skin. It is patient cartography. We know this method surprises us because it already has. When NASA's Interstellar Boundary Explorer first drew an all-sky map using these messengers more than a decade ago, it found a luminous ribbon arcing across the heavens, a narrow swath of enhanced neutrals that theory hadn't predicted. The ribbon appears to be ordered by the magnetic field of the local interstellar medium. Lines of sight where that field lies sideways to us glow brighter, as if the galaxy outside had painted a sign across our border. It was a beautifully humbling moment. The shape of our shield carries the fingerprint of the space around it. IMAP's finer energy steps and wider dynamic range are built to probe that signpost in detail, to test whether the ribbon is formed by so-called secondary neutrals particles that are born, charged again, and born once more, or by some other choreography at the seam between winds. To see the boundary is one wonder, to hear beyond it is another. The old Voyagers, now resident in the very local interstellar medium, detect the plasma out there by the music. It makes narrow bands of plasma oscillations that reveal the electron density of the space between stars. After Voyager 1 crossed the heliopause in late August of 2012 and Voyager 2 in early November of 2018, both heard a steadier, denser note than within the heliosphere. That shift in tone from the sparse outer wind to the thicker interstellar plasma is one of the clearest signs that the door had been opened. IMAP's maps on the inside and the Voyager's soundings on the outside will be woven together to locate, season by season, where the door sits and how it moves. If you picture a bow shock ahead of our star, a cliff of broken water, think again. Data from IBEX and supporting analyses showed that the sun's motion through the local cloud is too gentle and the interstellar magnetic field is too firm to permit a true shock. What forms appears to be a broader, softer bow wave, a pressure ridge rather than a breaker. It is a delicate thing, and IMAP's energetic neutral atom maps, layered across energies, should reveal how that ridge swells and thins across the solar cycle. Even the outline of the bubble itself is being rewritten. For decades, our sketches showed a long cometary tail streaming behind the sunday, then models that treat pickup ions, the hot recently created ions that dominate the outer wind's energy, as a distinct fluid, suggested a compact deflated croissant, instead with twin jets constrained by magnetic tension and a stubbier, more braided hinterland. IMAP's global multi-energy mapping, together with those Voyager waypoints, is precisely what is needed to test whether our home is a long streamer or a Titan pastry. Either way, the point holds magnetism, sculpts as surely as wind. There is practical grace here. The same boundary that carries a cosmic fingerprint also regulates the radiation that reaches us. Our bubble modulates galactic cosmic rays, the charged debris of distant cataclysms, thickening the shield when the sun is active and thinning it when the sun is quiet. IMAP's vantage at the first Lagrange point allows real-time sampling of the solar wind, as well as the returning neutrals, so forecasts for astronauts and for our fragile technologies can be sharpened. It is not overstatement to say that habitability has a magnetic and meteorological dimension, and that the architecture of the heliosphere is part of the reason we can think and speak beneath this sky. And there is the exquisite detective work of Origins. Parker's solar probe has shown us that the wind is not born smooth. It is flicked into motion by switchbacks and jets rooted in magnetic reconnection, lower down in the atmosphere, and on certain orbits the spacecraft has flown below the Alphen critical surface into plasma still in causal contact with the Sunday. Those near-sun birthmarks propagate outward and shape the large-scale flow. What IMAP sees at the frontier and what the Voyagers hear beyond it must ultimately be consistent with what Parker witnesses at the source. It is a single river seen at headwaters, midstream and mouth. So when a tiny neutral atom clicks in a detector near 1 million miles sunward of Earth, you can imagine the story. It carries a journey from a jet on the sun out across a living wind, a transformation at the wavering border, and a straight return months later to our waiting counters. Multiply that by millions and you have a breathing atlas of the edge of home. In the next part, I want to lean into what this atlas means for us, for cosmic rays and climate in space, for the safety of explorers, and for the wider idea that other stars carry their own magnetic cocoons. If habitability is in part a story of shelters, then our little shelter teaches us how to look for others' shelters then. If you think of the heliosphere as a great breathing tent, stitched from magnetism and wind, its purpose becomes clear. It softens the hail of high-energy particles that sweep in from the galaxy, and it sets the weather of space in which worlds must live. When the sun's magnetic field waxes over the familiar 11-year cycle, the tent thickens. Fewer galactic cosmic rays can thread their way to the inner system. When activity wanes, the fabric slackens, and more of those ancient messengers find us. That slow inhale and exhale is not a curiosity. It is a quiet regulator of risk for spacecraft, for astronauts, and for the delicate chemistry of atmospheres. It helps to be precise about what the shield means. Earth is doubly blessed, wrapped first by the heliosphere and then by its own magnetic cocoon, the magnetosphere, which turns the solar wind aside and shelters the upper air. But venture beyond that second cocoon toward the Moon and Mars, and you feel the galaxy more directly. The radiation field there is a tapestry woven from solar storms, the steady drizzle of galactic cosmic rays, and the state of the heliosphere itself. If you want a civilization that travels, you must learn to forecast that tapestry. This is where a sentry at the first Lagrange point, watching the wind that flows out and the energetic neutral atoms that fly back from the frontier, earns its keep, because it turns the abstract into a daily chart, a practical map of exposure and hazard. IMAP's genius is that it treats the edge of home like weather. 10 instruments tuned across a wide span of particle types and energies separate the murmurs of pickup ions from the shouts of faster populations, measure the glow of interstellar hydrogen and helium in far ultraviolet light, and listen to the magnetic field as it twists and relaxes. A photometer called GLOWS reads the faint helioglow, the scattered Lyman alpha light of neutral atoms drifting through our system, while telescopes such as SWAPI and HIT take the pulse of ions from the solar wind and from beyond. All of this is gathered near the first Lagrange point, a quiet perch, a little sunward of Earth where upstream conditions can be sampled in real time and compared with the returning neutrals that carry news from the frontier. The result is an atlas that breathes with the cycle and can be used day by day to refine what we tell explorers about the road ahead. But the story is larger than our own tent. Other stars blow other winds. They inflate their own astrospheres, larger or smaller, tighter or looser, depending on the vigor of the star and the temper of the surrounding cloud. For years, the most sensitive way to weigh those winds has been to look for a subtle bite in the Lyman alpha line of hydrogen, a signature of extra absorption in the hydrogen wall where a star's wind presses into the interstellar medium. That method has shown that some nearby sun-like stars shed mass at rates comparable to or far exceeding our stars, implying astrospheres that could be markedly different from our own. More recently, astronomers have begun to glimpse these shelters in other wavelengths, soft X-rays from charge exchange at the astroperic boundary, offering an independent luminous confirmation that winds sculpt cocoons wherever there is a star with breath to spare. For planets tucked within those cocoons, the radiation climate, and thus a portion of habitability itself, will depend upon the size, shape and health of that invisible shelter. This is where our local geography becomes important. The sun does not drift through a uniform fog. It sails through a patchwork of interstellar clouds, each with its own density, temperature and magnetic mood. Today we reside in the local interstellar cloud, a partially ionized wisp that we traverse at tens of kilometers per second. The boundary of that cloud lies close enough that in astronomical terms we may graze its edge in the not too distant future. Beyond it may lie a region with different pressure and field, and therefore a different fit for our bubble. That means the heliosphere is not only modulated from within by the solar cycle, it is also tailored from without by the medium through which we pass. Home, in other words, is a moving target. IMAP's maps and the Voyager soundings let us watch that tailoring in action. As energetic neutral atom images accumulate the bright ribbon first discovered by IBEX, the skywide signpost, likely ordered by the local interstellar magnetic field, can be traced across energies and seasons, its intensity, compared with the cycle and with the plasma density that the Voyagers hear outside. In time, we will learn whether the ribbon is dominated by so-called secondary neutrals born just beyond the heliopause, or by some other choreography at the seam, and whether its knots and curls record the texture of the cloud we are entering as surely as beach ridges mark ancient tides. The point is not merely aesthetic. The ribbon is a diagnostic of how firmly the galaxy is pressing on the walls of our tent. There is a satisfying unity to this enterprise. Parker Solar Probe has flown low enough to feel the places where the wind is flicked into being beneath the Alphen critical surface, where motions remain tied to the magnetic field of the star. The Voyagers have drifted beyond the heliopause and heard the denser, steadier tone of the very local interstellar plasma. Between them, stationed upstream of Earth IMAP works as a translator. It takes the language of birth and the language of beyond and renders them into a common map, a steadily improving picture of how a star carves out a refuge for its planets and how that refuge sustains or surrenders under pressure. That is the beginning of a comparative science of shelters, one that we can carry to other suns. And because this is not just philosophy but engineering, there are dividends close to hand. Better particle maps at the edge of home sharpen our understanding of how galactic cosmic rays are modulated before they reach this lunar space. Better upstream solar wind measurements improve the forecasts that protect satellites, power grids and pilots. And a clearer grasp of the heliosphere's geometry helps us design voyages beyond the magnetosphere with realistic expectations of dose and danger. The boundary that poets call beautiful is in practice a piece of safety equipment. Still, I cannot resist the poetry. We are a small civilization in a vast sea, and yet we have learned to watch the tide on the far horizon and to infer from a flicker of ultraviolet light or a handful of returning atoms the changing fit of the world that holds us. In the next part, I want to fold this back to the human scale, to follow a notional expedition outward past the magnetosphere, past the orbit of Mars into the heliosheath itself, and to imagine what explorers will feel and measure as the sun's breath thins, the cosmic chorus rises, and the map we have made from afar becomes the landscape under their feet. Picture us in a small craft, unhurried, slipping sunward to starboard, so that Earth's soft aurora fades behind us, and the background becomes a darker, purer blue-black. I like to imagine the instruments murmuring in the cabin, magnetometers ticking like a metronome, ion counters pattering like rain, a photometer counting far ultraviolet photons one by one. At first, the solar wind is a brisk river. Its electrons and protons move supersonically, streaming along that spiraled field that Parker and his successors traced so beautifully, switchbacks and all. Far inside Parker Solar Probe has shown us that the river is born unruly, a tangle of magnetic flips and jets. Out here, the turbulence has grown long, limbed and musical, but it is the same song. The closer passages through the corona where Parker dipped beneath the Alphen critical surface are the headwaters of the story we are sailing into now. Hours become days, and the river slackens almost imperceptibly until somewhere beyond the orbit of the giant planets, a cliff in the mathematics is reached. The flow yields from supersonic to subsonic. That change, silent to the ear but unmistakable on the dials, is the termination shock. Voyager 1 first felt it in December 2004 at about 94 astronomical units from the Sun. Voyager 2 met it in August 2007, nearer 84 astronomical units, a reminder that the boundary breathes and buckles with the solar cycle and the interstellar weather. What lies beyond is the heliosheath, the Sun's outermost breath, slowed and heated a buffer, where pressures negotiate and particles are accelerated. In that buffer, a different population takes charge. Neutral atoms from interstellar space wander inwards until sunlight charge, exchange or electron impact ionizes them. At that instant, they are picked up by the solar wind's magnetic field and flung into its flow. By the time we reach the outer heliosphere, these pickup ions carry much of the internal pressure. They soak up energy at shocks and they dominate the thermodynamics of the sheath. It is a lovely inversion. Outsiders become stewards of the boundary. The picture that has emerged in recent years through in situ measurements and theory is that pickup ions shape the heliosheath structure and even mediate shocks themselves. The magnetic field here is restless. If you were to plot its strength minute by minute, you would see a sawtooth script written by turbulence with spectral slopes that speak of cascades and intermittency. Voyager's magnetometers have traced those fluctuations in detail, catching both compressive and non-compressive variations and revealing a heliosheath that is anything but smooth. The field's changes modulate cosmic rays. Increases and decreases in the field's strength dim and brighten that cosmic rain even out here. This is not a static wall but a breathing complex medium. Press further and another transition awaits the heliopause, where the Sun's influence gives way to the interstellar plasma. When Voyager 1 crossed it in late August 2012 and Voyager 2 in early November 2018, neither encountered a dramatic jolt so much as a change in the music. The density of the plasma beyond is higher, and it sings through the spacecraft's plasma wave instruments as a clear, sustained tone. Those tones have mapped a gentle gradient in density across tens of astronomical units beyond the boundary proof that we are listening not to vacuum, but to a tenuous ocean. On our imagined voyage, we pause before that frontier, lingering in the helio sheath where acceleration thrives. Here, the long, mysterious, anomalous cosmic rays atoms that began as interstellar neutrals were picked up and then boosted to hundreds of mega electron volts find part of their origin story. The termination shock is not a single, simple engine. Stochastic processes in the sheath contribute, and the geometry of the shock itself is blunt and variable. The lesson the Voyager's taught is subtle acceleration is distributed. The sheath is a factory floor, with many stations, and pickup ions are the raw material. If we look up from our dials to the wider sky, another kind of map can be made. Even as we sit within the sun's breath atoms born at the frontier, energetic neutral atoms created when fast ions steal electrons from interstellar neutrals fly straight back toward the inner system. Catch enough of them sought by energy and an image of the boundary emerges. This is what the Interstellar Mapping and Acceleration Probe now does from its perch near the first Sun-Earth Lagrange point. A triad of energetic neutral atom images spanning low to ultra-high energies, a magnetometer to hear the field close to home telescopes for ions and electrons, a dust counter, and a tiny photometer called the Global Solar Wind Structure Instrument that counts far ultraviolet Lyman and alpha photons from interstellar hydrogen, tracing the helioglow. The instrument suite is a weather station for the edge of home, and after its September 2025 launch, it set course for that quiet perch a million miles sunward of Earth. Those maps will refine a picture already changed by earlier work. A decade or more ago, the Interstellar Boundary Explorer drew a luminous ribbon across the sky. An arc of enhanced neutral atoms aligned its seams with where the local interstellar magnetic field lies sideways to our view. The ribbon said in one graceful stroke that the galaxy beyond leaves its fingerprint on our border. Its very existence also sharpened another emerging truth rather than a fierce bow shock before the sun's prow. There is likely a gentler bow wave, a pressure ridge shaped by a relatively modest interstellar flow and a firm external magnetic field. The edge of home, it turns out, is a negotiator rather than a battering ram. Models of the whole bubble have changed with the data. For decades, we drew a long cometary tail. Then careful consideration of magnetic tension and the role of pickup ions suggested a more compact deflated croissant with twin jets folding back. I find that phrase as pleasing as the physics. The pastry is shaped by magnetic tension, the jets by the field's grip, and the entire form responds to the deep rhythm of the solar cycle. Interstellar Mapping and Acceleration Probe, with its wide energy coverage, IMAP ultra-alone images, neutral atoms of several to a few tens of kilo electron volts across large swathes of sky every few months, will help decide how stubby or how braided our tail truly is. For an explorer, all this is not merely aesthetically satisfying, it is practical. The radiation climate of deep space is a tapestry woven from solar storms, the slow modulation of galactic cosmic rays by our changing bubble, and the state of the sheath. Forecasts for astronauts beyond Earth's magnetic cocoon depend on understanding these threads. By sampling the solar wind upstream and the returning neutral atoms from the Frontier Interstellar Mapping and Acceleration Probe, turns delicate physics into daily guidance. It is one of those rare missions that speaks to poetic curiosity and to engineering caution in the same breath. Pause again at the boundary and listen to what lies beyond. The very local interstellar medium is not empty. Voyager's plasma wave instruments hear it as a gallery of narrow tones, a sustained chorus whose frequency tells us the electron density out there is a few hundredths to a tenth per cubic centimeter, gently varying across tens of astronomical units. When pressure pulses from the sun, coronal mass ejections roll outward. They can send ripples that Voyager hears even in interstellar space like distant surf booming on an unseen shore. The inside and the outside are in conversation. And so our little craft loiters at the threshold, with the sun's long exhalation rushing past the hull and the galaxy's thinner air just beyond. In the next stretch of our journey, I want to lift our eyes from the border to the waters we are entering, the local interstellar clouds, their temperature and magnetism, the hydrogen wall that glows in Lyman alpha, and the way our course through that patchwork can tighten or loosen our bubble, because before we step fully into interstellar space, it helps to know the tides. Lift your eyes now to the waters we're entering, the very local interstellar medium, a patchwork of clouds and cavities like shoals and slow lagoons on a continental shelf. We sail inside the local bubble, a broad, low-density cavity likely carved by ancient supernovae, and within that hollow we traverse a denser wisp called the local interstellar cloud. The LIC is warmed thousands of degrees by temperature but whisper-thin by density, and it carries a modest magnetic field that presses on our bubble from without. The geometry matters because the field outside helps decide how tightly the heliosphere is cinched and where its boundary brightens. Recent mapping work even reimagines the local bubble as a chimney-like structure in 3 dimensions, another reminder that empty is rarely simple. The LIC is not forever. Along certain sightlines we see little or no lick absorption, a sign that we are near its edge, and several reconstructions suggest the sun will leave this cloud in a few thousand years. An eye blink, geologically, a heartbeat. Cosmically, crossing into a neighbouring parcel with a different pressure or magnetic mood would retune the heliosphere. It could tighten our cocoon or loosen it, change the cosmic ray climate and alter the fit of home. There are even scenarios in which a denser, colder filament could briefly press our bubble hard enough to let interstellar atoms reach deeper inside. That is not a prophecy but a sensitivity test. The shield we live within is exquisitely responsive to the weather of the space around it. Where the wind we blow meets the air, we sail through hydrogen piles. Up in a gentle ridge, astronomers call it the hydrogen wall. You cannot see it with your eyes, but starlight feels it. In far ultraviolet spectra, a faint extra bite appears in the hydrogen line and alpha line along nearby sightlines. That extra absorption was the first remote sign that our heliosphere paints a luminous seam where it meets the interstellar flow. Over the years, careful modelling split the signature into 2 contributors, atoms heated and slowed in the wall itself, and atoms from the broader heliosheath within. In that subtle shape is a gauge of how firmly the galaxy is pressing on us today. And the wall glows not just in pencil-thin beams from bright stars, but across the sky as a diffuse helioglow. New Horizons, far beyond the orbit of Pluto, carries a far ultraviolet spectrograph called ALICE. By counting Lyman alpha photons scattered from interstellar hydrogen streaming through our system, it has drawn the first wide maps of that glow from the outer solar system. Those maps trace the inflow of the local gas, the brightness of the hydrogen ridge, and the way the heliosphere breathes with cycle and season. In concert with near-Earth sentries IMAP among them, this remote view helps pin down the density and flow of the very local medium that shapes our shore. One stream in that inflow is particularly telling: interstellar helium. Unlike hydrogen, helium is less perturbed by solar radiation pressure, so it wafts through our system with a steadier hand. Inside Earth's orbit, it forms a focusing cone, a gentle downstream enhancement that turns up predictably each year. The Ulysses mission and later IBEX used that cone to weigh the speed and direction of the interstellar wind. In the process, they uncovered hints of a secondary helium population atoms, born and processed in the outer heliosheath, that complicates the story in the most useful way. Those subtleties are not footnotes, they are fingerprints of boundary physics. The field outside is not an abstraction. IBEX found a luminous arc, the ribbon of energetic neutral atoms draped across the sky, brightest where our lines of sight lie perpendicular to the local interstellar magnetic field. That simple, astonishing fact ties the shape of our border to the direction of the field a few dozen parsecs around us. Follow-up analyses have refined the field's orientation using the ribbon's extraordinarily circular center and compared it with other traces like the polarization of starlight by interstellar dust. The upshot is elegant. The local field is coherent on neighborhood scales, and the heliosphere is a windsock that faithfully records its direction. IMAP will interrogate that signpost with finer energy steps season by season to learn whether the ribbon's glow is dominated by secondary neutrals just beyond the heliopause or by another choreography entirely. Fold all this together and you get a picture of tides, cosmic ones. The sun's 11-year rhythm pumps our bubble from within. The cloud's density, temperature, and field lean on it from without. And at their seam, the hydrogen wall glows while neutral messengers fly back toward our waiting detectors. That is why understanding the shore is not poetic license, but practical navigation. Radiation dose for explorers beyond Earth's magnetosphere depends on whether the heliosphere is taut or slack. The seasonal drift of the helium cone and the brightness of the Lyman alpha glow reveal how firmly the interstellar wind is blowing. And the ribbon's quiet arc tells us which way the larger field is combed across our neighborhood. These are the dials on the wheelhouse as we steer. So as our imagined craft idles in the outer wind and we study the glow on the horizon, keep the scale in mind: a handful of atoms per cubic centimeter, a field only microgauss strong. temperatures counted in thousands of degrees, but also tenuous, that a human breath holds more substance than miles of space. Yet out of such gossamer, a shelter is made. In the next part, I want to bring that shelter back to the scale of worlds, how planets feel these tides differently depending on their own magnetic cocoons, and what our growing atlas of astrospheres suggests about the quiet necessary for life around other suns. Back to worlds then. 3 ways of being sheltered beneath the same Sunday Earth is doubly wrapped first by the heliosphere and then by its own magnetic cocoon. Together with our thick air, that magnetosphere takes the brunt of the gale-bending particle streams, storing them in luminous belts and letting most of the worst of space weather slip past. It is not a rigid dome, but a living shield that flexes with storms. Still for life at the surface, it lowers the cosmic rain to a soft drizzle. Step just outside that second cocoon and you feel the difference in your bones, quite literally. On the Moon, which lacks both a global magnetic field and a substantial atmosphere, instruments have now measured the ambient dose from space radiation directly. The Lunar Lander Neutron and Dosimetry experiment reported an average dose equivalent of about 1.3 millisieverts per day at the surface, roughly 200 times Earth's ground level background, and in line with independent estimates of about 60 microsieverts per hour from other teams. The numbers vary with solar activity, but the lesson is firm: without a sky that holds and a magnet that bends the galaxy reaches you. Mars sits between these cases, a world with only a wisp of magnetism left in its crust and an atmosphere too thin to cushion much. Curiosity's radiation assessment detector found a typical surface dose near 2/3 of a millisievert per day, and during cruise to Mars the rate was closer to 2 millisieverts per day, reminding us that deep space beyond Earth's magnetic reach is harsher than a planetary surface, even a tenuous one. These are averages. The sun's temper can swell or calm them, and so will the state of our biggest shield, the heliosphere. Why is Mars so exposed? Partly because it lost the refuge that Earth kept. The MAVEN mission has shown piece by careful piece that the solar wind has been gnawing at Mars for eons. Under today's gentler sun, the spacecraft still sees oxygen and other ions accelerated and stripped away. And when researchers comb through nearly a decade of data, they confirm sputtering energetic particles, kicking atmospheric atoms up and out as a key escape route in the planet's youth when the sun was more violent. Subtle cumulative weathering by the stellar wind can over time turn a warm, wetter world into a dry one. And yet not every world needs a geodynamo to have some kind of shield. Venus, so like Earth in size, so different in fate, has no global magnetic field, but its dense ionosphere can at times push back. The solar wind's embedded field drapes around the planet, and an induced magnetosphere flickers into being complete with a long magnetotail. It is a leaky umbrella, and ions still escape under the pressure of storms, but it is a reminder that magnetism can be borrowed from the wind itself. For explorers, these distinctions are not academic. NASA's radiation standards and planning tools divide the threat into 3 chords of the same music: the steady drizzle of galactic cosmic rays, the sudden squalls of solar energetic particles, and the trapped particles that haunt certain orbits. Deep space voyages must reckon with all 3, and they do so against the shifting backdrop of the heliosphere's own cycle. Thicker in active years, thinner in quiet ones. That is one of the reasons a century at the Sun-Earth First Lagrange point that samples both the outbound wind and the returning neutral messengers is so valuable. It turns the poetry of shelter into a practical forecast. Now lift the idea from our backyard to the stars. Other suns blow other winds. They sculpt astrospheres, magnetic tents that swell and slacken with activity and with the interstellar weather of their neighborhoods. You cannot easily weigh those winds directly, so astronomers learned a gentler trick: watch the far ultraviolet Lyman alpha line of nearby stars and look for an extra nibble of absorption from a hydrogen wall where neutral interstellar atoms pile up just outside the astrosphere. That tiny deficit in starlight, seen with space telescopes, has become one of the only reliable ways to estimate mass loss from sun-like and cooler stars, and by inference the size of their shelters. What those measurements and models say is that shelters differ wildly. Reviews of astrospheres around cool stars show some bubbles ballooning to thousands of astronomical units, and others pinch tight depending on wind vigor and magnetic geometry. The upshot for habitability is simple. The radiation climate of a planet depends not only on its own magnetosphere and air, but also on the health and posture of the larger tent drawn by its star. In some systems, cosmic rays will be filtered well upstream. In others, the galaxy will press far closer to the worlds we might one day map. Consider the small red suns, the M dwarfs around which so many rocky exoplanets are found. Their habitable zones are tucked close in where the wind is stronger and the X-ray and ultraviolet glare more intense. Simulations for Proxima Centauri's planet suggest stellar wind pressures thousands of times Earth's, with the magnetopause of any Earth-like field pulsing dramatically over the course of a single orbit. Add frequent flares and possible coronal mass ejections, and atmospheric escape can accelerate, especially from the upper layers heated by extreme ultraviolet light. It is not a verdict against life, but it is a counsel of realism. Some small suns may be noisy neighborhoods. Even within this demanding company, there are paths to quiet. Climate models for Proxima b, for instance, explore worlds with oceans and winds that redistribute heat, and magnetohydrodynamic studies map when space weather might be calm enough that a planetary field can hold the line. The new discipline here is comparative shelter. Take what we are learning about our own boundary, the role of pickup ions, the imprint of the external magnetic field, the seasonal breathing of the hydrogen glow, and carry those lessons into the modeling of other stars' cocoons. In that way, a mission that maps our shore also becomes a tutor for distant coasts, and all the while the human thread runs through it. Radiation monitors on rovers and orbiters give us daily dose rates. In places we will one day work about 2/3 of a millisievert per day on the Martian surface under typical conditions, a little over 1 millisievert per day on the moon numbers that tighten or slacken as the heliosphere itself breathes. Fold those into the guidance that protects crews and machines, and the heliosphere stops being an abstraction. It becomes a line on your mission plan: when to go, what to wear, how long to linger. So the lesson of shelters, from Earth's steadfast magnet to Venus's borrowed one, from Mars's lost to the embattled worlds of red suns, is that habitability is a choreography between local and global tents, between a planet's own field and sky, and the larger cocoon its star blows into the interstellar breeze. In the next part, I want to draw that choreography into a field guide for travelers, how we read the dials of the heliosphere and the local cloud together, cosmic rays, hydrogen glow, the ribbons arc to choose our season for outward journeys, and what IMAP's first maps can teach us about the safest paths across the sun's moving sea. A field guide then for travelers reading the sky by touch as much as by light. If I were plotting an outward voyage, I would begin with the slowest dial of all the 11-year rhythm of our star. In active years, when the solar wind is muscular and the magnetic field is wound tight, the galactic drizzle thins. In quiet years, the drizzle strengthens. That anti-correlation is not folklore. It is the long-studied modulation of galactic cosmic rays by the heliosphere's changing field and flow. For deep space journeys, it translates into a seasonal choice travel, near a solar maximum, to enjoy fewer galactic cosmic rays but accept a greater chance of sudden solar storms. Or choose solar minimum when the background climbs, but the sun is on average less explosive. The physics is settled, the judgment is human. The next dial is quicker and more capricious, the storms themselves. Solar energetic particle outbursts ride with flares and coronal mass ejections, and they can raise radiation by orders of magnitude for hours to days. We cannot yet predict them with the confidence we would like, but we have learned that their likelihood swells around the crest and especially on the declining shoulder of a solar maximum. For mission planners, that means shelters, contingency routes, and an ear to the upstream monitors that warn of approaching shocks. Those upstream sentries are now a small flotilla. At the first Sun-Earth Lagrange point, a little sunward of Earth, the interstellar mapping and acceleration probe IMAP spins and listens, counting the outward wind in real time while building global maps of the heliosphere from returning energetic neutral atoms. Its 10-instrument payload includes a pair of high-energy neutral atom imagers, IMAP Ultra 2, IMAP High sensors for the mid-energy band, and IMAP Low for the coolest messengers, complemented by solar wind and pick-up ion spectrometers, a magnetometer, and the global solar wind structure photometer GLOWS that counts far ultraviolet, Lyman alpha photons from the helioglow. This is not mere ornamentation, it is a traveller's barometer for the edge of home. IMAP launched in late September of 2025 with two companions, the Carruthers Geocorona Observatory and NOAA's space weather follow-on at Lagrange 1, and is now on station. That rideshare matters. NOAA's follow-on observatory, newly rechristened for operations, keeps a 24-hour watch on the sun's outer atmosphere, and the wind itself relaying data to forecasters who issue practical warnings for satellites' power, grids and crews in transit. Together with IMAP translating the far frontier into sky maps, and Carruthers tracing Earth's great exosphere, the Lagrange 1 trio turns poetry about the shore into an operational chart. Now, a quieter dial, one I find almost meditative, New Horizons far beyond the giants, has been sweeping the sky in Lyman Alpha, the ultraviolet whisper of hydrogen. By subtracting the sun's own scattered glow, the ALICE spectrograph has yielded wide maps of that diffuse background, a soft illumination that traces, among other things, the structure of the local bubble around our system. For a voyager, this is not simply pretty, it is a way to sense the density and disposition of the gas we are sailing into, because that gas shapes the fit of our heliosphere and the brightness of the hydrogen wall at its edge. Closer in a yearly pulse marks our passage downstream, the helium-focusing cone. Interstellar helium drifts through the heliosphere, comparatively undisturbed, and piles into a gentle cone on the downwind side of the sunday. As Earth crosses that cone each year, instruments see the helium brighten. Ulysses first charted it, and Ibex refined the geometry. For a field guide, the cone is an annual breadcrumb, a way to confirm the interstellar wind's direction and temperature, and to check whether the local stream is changing as we graze the edge of one cloud and enter another. And then there is the ribbon, a luminous arc in energetic neutral atom light discovered by the Interstellar Boundary Explorer more than a decade ago, hanging across the sky where our line of sight lies perpendicular to the local interstellar magnetic field. It is a signboard painted by the galaxy outside, and its slow breathing across energies and seasons is a measure of how tightly the field beyond is cinching our bubble. IMAP's first global images, with finer energy steps and wider dynamic range, will interrogate that sign. Even before the detailed atlases arrive, the intent is clear. Trace the ribbon's changes, and you trace the pressure of the medium we are entering. All of this telemetry can be folded into a traveler's rule of thumb. If your voyage is short and remains near the protection of Earth's magnetosphere, you favour quiet days regardless of where the solar cycle sits. You watch the coronagraphs for fronts, the in-situ monitors for shocks, and you mind the nowcasts. If your voyage is long and commits you to deep space, you consider sailing nearer the crest of the cycle to trim the persistent bite of cosmic rays while hardening your plans against the squalls. The literature makes the trade plain lower galactic background at solar maximum, higher risk of episodic solar energetic particle storms, higher background at minimum, fewer catastrophic outbursts on average. No choice erases hazard. The art is to choose the flavour you can best mitigate. And there is a final oddly musical dial that I would keep half an ear upon the chorus outside. The Voyager spacecraft adrift beyond the heliopause hear the very local interstellar plasma ring narrow persistent tones whose pitch tells us the electron density in the space beyond our bubble. When great pressure pulses leave the sun and move outward, those tones shift. In that way, the inside and the outside converse, and we can tell when the tide is rising at the frontier. I like the thought of a helm guided by such a sound. Field guides end with checklists, so here is mine. Read the cycle sunspot counts and the slow swing of cosmic ray neutron monitors which brighten in quiet years and dim in active ones. Watch for Forbush decreases those sudden drops in neutron counts that herald a passing shock and treat them as the swell before the storm. Fold in the Lyman alpha maps from the outer system and the annual helium cone crossing to gauge the interstellar wind. Overlay the ribbon's arc to feel the pull of the field outside. And bind it all to the real-time breath of the solar wind from the Lagrange 1 sentries. IMAP, the Space Weather Observatory, and the Geocoronal Scout, so that the poetry of shores becomes a route you can fly. In the next stretch, I want to take that checklist aboard our imagined craft and sail it outward in earnest, plotting a line past the orbit of the giants toward the heliosheath, and asking with each instrument's whisper how the map we made from afar begins to match the living water beneath our keel. Set the checklist on the console and ease the throttle. This is how I'd actually fly it. We begin by lacing our own measurements to the big patient maps coming in from the centuries sunward of Earth. Interstellar mapping and acceleration probe, sitting near the first Sun-Earth Lagrange point, spins like a lighthouse and sweep by sweep turns, returning neutral atoms into weather charts for the edge of home. 10 instruments share the work: low, mid and ultra-high energy neutral atom images, telescopes for solar, wind and pickup ions, a magnetometer, and a tiny photometer called GLOWS that counts far ultraviolet Lyman alpha light from drifting interstellar hydrogen and helium. Think of it as a barometer for the frontier, reading both the breath that goes out and the whispers that come back. Because IMAP launched together with two companions, NOAA's Space Weather Follow-On bound for the same Lagrange perch and NASA's Carruthers Geocorona Observatory, our little ship at once benefits from a triad real-time upstream, solar wind and coronal imagery from SWFO, a global read on Earth's vast exosphere from Carruthers, and the long baseline frontier cartography from IMAP. A field guide needs all three storm warnings, local sky and the far horizon. With those charts in hand, set course for the outer system. As we slide past the giant planets, the background drizzle of galactic cosmic rays rises and falls with the solar cycle. The heliosphere's modulation is strongest when the sun is active and weakest when the sun is quiet. That slow breathing is not poetry, it is measured physics, the grand anti-correlation recorded by monitors and missions over decades, and now folded into IMAP's synoptic view. We choose our season accordingly, travel nearer the crest for fewer galactic rays but more chance of sudden squalls, or go in the trough for a calmer sun but a higher background. The sky's temperament becomes a navigational parameter, then the quick dials storms. On any given day, the risk to crew and craft is set not only by the gentle rise and fall of the cycle, but by the probability of a sharp front solar energetic particles riding ahead of a coronal mass ejection. The new Space Weather Sentinel at Lagrange 1 watches the solar atmosphere and the wind continuously, while IMAP samples the charged particle C and the returning energetic neutrals that betray distant pressure ridges at the border. Even a traveller's superstition, never cross open water, on a rising wind, begins to sound like sober flight dynamics with this telemetry in hand. By the time we are well beyond the orbits of the giants, the edge of home ceases to be a sketch and becomes a measurable coastline. There, the voyagers taught us the order of transitions. First, the wind decelerates from supersonic to subsonic at the termination shock. Then comes the warm, turbulent heliosheath. And farther still, the heliopause, where the sun's influence thins and the interstellar plasma takes over. Each step was heard not as a bang, but as a change in music. Beyond the heliopause, narrow plasma tones reveal the denser, steadier interstellar medium. Our ship sails with that expectation because those two elder craft went first, and now a delight of method. At the far frontier, a charged ion can steal an electron from a neutral interstellar atom and become an energetic neutral atom, free to fly straight immune to magnetic fields. IMAP turns those straight-flying messengers into a global image energy by energy. Earlier, a small pathfinder called IBEX drew the first such maps and found a luminous arc, the ribbon, where sightlines perpendicular to the local interstellar magnetic field glowed brighter than theory expected. That single elegant surprise told us the galaxy outside imprints itself on our border, and it gave us a sky-fixed sign to watch as the solar cycle and the local cloud change. IMAP was built to resolve the ribbon's anatomy across finer energy steps and wider dynamic range, to test whether so-called secondary neutrals and retained ions are doing the painting. The ribbon is not the only cartographer's gift. Far beyond Pluto, New Horizons has been sweeping the sky in Lyman Alpha, the ultraviolet whisper of hydrogen, and has assembled the first wide maps of that glow from its vantage in the outer darkness. Those data trace the inflow of very local gas, the brightness of the hydrogen wall, where our wind meets the interstellar breeze, and the way the heliosphere breathes across the cycle. Fold that glow into IMAP's particle-made images, and you begin to see both outline and waterline, shape and pressure together. Meanwhile, closer to the furnace, Parker Solar Probe keeps telling us what the wind is like at its birth. It has dipped beneath the Alphen critical surface and traced magnetic switchbacks, zigzags in the field, back to funnels on the sun's visible surface, showing that the fast wind is at least in part powered by those structures. What is born jagged and impulsive is heard again hundreds of times, farther out as long-limbed turbulence in the heliosheath, the headwaters and the mouth of the same river. That continuity matters when we try to match the ripples in our in-situ data to the texture in IMAP's global maps. There's a practical cadence to all this. Each morning you would pull down the Lagrange 1 telemetry, solar wind speed, density, temperature and field from the Space Weather Observatory. Neutral atom counts from IMAP split into low, mid and ultra bands, and geocoronal context from Carruthers. You would compare the newest frontier maps to the slowly shifting arc of the ribbon and to the soft ultraviolet background New Horizons reports from its Deep Space Watch. And you would dial all of that against the slow swing of the cycle. The result is not a single prophecy, but a probabilistic sea state for the week ahead. If you ask what anchors these expectations beyond charts and models, I point back to the two old voyagers. Their instruments have chronicled both sides of the heliopore's dips and surges in energetic particles at the crossing and beyond the steady chorus of interstellar plasma. Even as power is husbanded and instruments are retired to keep them alive, the data remain the reference track for any ship that follows. When IMAP's maps say the frontier brightened at certain energies and the voyagers hear a pressure pulse months later, you have the exquisite satisfaction of triangulation. So we sail on not guessing but listening, calibrating our hull against the sky's breath, treating the heliosphere as weather rather than wallpaper. In the next stretch, I want to stand on that outer beach itself, the heliosheath, and walk its physics in detail, how pickup ions seize the thermodynamic budget, how anomalous cosmic rays are manufactured by many small engines rather than one, and how the very shape of the bubble, the old comet's tail or the magnetic crescent, emerges from the tug of war between flow and field. We are standing in imagination on that outer beach, the heliosheath, where the sun's great river has slowed and warmed and begun to negotiate with the sea beyond. What the voyagers taught us first is almost cheeky in its simplicity. The particles that did not begin here now run the show here. Interstellar atoms drift inwards as neutrals, and once ionized are picked up by the solar wind's magnetic field. By the time you reach this buffer, those pickup ions hold most of the thermodynamic budget. They soak up the energy lost at the termination shock and dominate the pressure that pushes against the galaxy. That picture emerged from the spacecraft data and from theory over decades, and it gives the heliosheath its character outsiders made stewards. The older expectation was that anomalous cosmic rays, those rare heavy atoms that begin as interstellar neutrals and are accelerated to hundreds of mega electron volts, would be forged right at the termination shock, like sparks flying from a tape whetstone. But when Voyager 2 met the shock, the intensities did not crest there, they built up downstream. The lesson was that acceleration is distributed, messy and alive, some done at the flanks, some in the broad heliosheath by stochastic processes, some in pulses and transients that come and go as the boundary itself flexes. It is a factory floor with many stations rather than a single engine. If you could listen to the magnetic field out here, you would hear it as a restless hiss, compressive and non-compressive fluctuations etched across minutes to hours. Voyager's magnetometers drew that script and found a turbulence that is not simply the inner solar wind stretched thin, but a river remixed by new waves excited by the newborn pickup ions. Even the way we interpret those fluctuations has had to evolve. The flow is subsonic here, so the usual trick of turning time into space, the Taylor hypothesis, begins to fail, and theorists have built new four-dimensional frameworks to read the spectrum honestly. It is an unruly medium, and yet within the unruliness, there is order enough to make maps. Walk a little farther and the beach becomes the line itself, the heliopause, where the sun's influence yields to the very local interstellar plasma. When the voyagers crossed years apart, they did not feel a jolt so much as a change in the music beyond the boundary. Narrow plasma tones rang out, and their pitch told us the electron density out there is tens of times higher than in the outer wind. It was one of the cleanest confirmations that the door had been opened. The interstellar ocean has a different note. Now about the coastline's shape. Textbooks long favoured the image of a comet's tail, a long streamer trailing behind the sundae. But as models began to honour magnetic tension and treat the hot pickup ions as a distinct fluid, another figure emerged, a compact deflated croissant with twin jets folding back under the grip of the field. It is not pastry for pastry's sake. It says that force lines sculpt the boundary as surely as mere flow, and that the balance between them changes with the cycle and with the neighbourhood through which we sail. Even ahead of our motion, the myth of a crashing bow shock has given way to something subtler. The sun is moving gently through a magnetised local cloud. The Mach number is low enough and the external magnetic field firm enough that the shock softens into a broad bow wave, a pressure ridge rather than a breaker. That revision came from the marriage of energetic neutral atom imaging with global modelling, and it has quietly redrawn the map for a generation. The edge of home, it seems, negotiates. It does not smash the galaxy aside. What turns these sketches into an atlas is a kind of particle astronomy. At the contact, charged ions can steal electrons from drifting neutrals and become energetic neutral atoms, free of magnetic fields flying straight. Count enough of those messengers by arrival, direction and energy, and the frontier paints itself. A small pioneer called the Interstellar Boundary Explorer surprised us more than a decade ago, with a luminous ribbon arcing across the sky, brightest where our sightlines are perpendicular to the local interstellar magnetic field. an elegant sign that the space outside imprints itself on our border. Interstellar Mapping and Acceleration Probe was designed to revisit that sign with finer energy steps and a wider dynamic range to test whether the glow is dominated by secondary neutrals born just beyond the heliopause, or by some different choreography at the seam. IMAP now on station near the first Sun-Earth Lagrange point carries 10 instruments for this work: low, mid and ultra-energetic neutral atom imagers, telescopes for solar, wind and pickup ions, a magnetometer, and a small, far ultraviolet photometer nicknamed GLOWS to read the helioglow in Lyman alpha. Its job is to turn the breathing of the heliosphere into weather charts to track season by season how pressure from within and without tightens and loosens the fabric. The promise is not only a prettier coastline, but a physically sharper one, a way to separate the contributions of hot pickup ions, cooler solar wind ions, and the firm hand of the external field. From still farther out, another quiet witness has joined the cartographers. New Horizons in the deep outer system has swept the sky in hydrogen's Lyman alpha glow and assembled the first wide maps of that ultraviolet background from its vantage beyond the giants. Those maps trace the inflow of the local gas and the brightness of the hydrogen wall where our wind meets the interstellar breeze. Fold that soft illumination into IMAP's particle-made portraits, and you begin to see not only outline but waterline shape and pressure together. If you ask me what single idea to carry from this beach, I would choose humility in the face of detail. The heliosheath is not a quiet moat. It is a dynamic mediator, where pickup ions take the energy where acceleration happens in many small theatres rather than one grand stage, and where magnetism sculpts as decisively as flow. It is tangled enough that an observatory must sort messengers by energy and season to see the pattern, and orderly enough that once sorted the pattern holds. That is why we build the sentry at the Lagrange point, and why we keep the voyagers listening beyond the gate. Together they turn a change in the music into a map you can sail by. And because every good beach is a threshold, our next step is obvious. We leave the sand of the heliosheath and row a little way into the very local interstellar medium itself out, where the plasma chorus is steady, the hydrogen wall glows faintly, and the sun's long exhalation finally falls behind us, and asks what kind of sea we are entering and how its tides will play upon the shelter we leave astern. Beyond the gates, the music changes. The plasma out here is cooler in temperament, steadier in tone, and yet alive with fine structure. When the first of the voyagers drifted across the heliopause, its plasma wave antenna began to hear a narrow, persistent whistle whose pitch betrays the number of electrons in the space between stars. Convert pitch to density, and you find a value of a few hundredths of a particle per cubic centimetre tenuous, beyond imagining but far denser than the outer solar wind. In later years, the same antenna kept hearing a quiet, continuous chorus, allowing us to track gentle rises and falls in that density across many billions of kilometres. It was the most delicate kind of confirmation that we had stepped into the interstellar sea. Name the waters, and they become more familiar. We are sailing inside the local bubble, a vast low-density cavity, probably carved by ancient supernovae, and within that hollow we are passing through a warmer filament called the local interstellar cloud. Its temperature is counted in thousands of degrees, its hydrogen density in a few hundredths to a few tenths per cubic centimetre, and it carries a modest magnetic field that presses on the walls of our heliosphere from without. The cloud is not uniform. Measurements toward nearby stars reveal patchwork structure, flows and eddies, and the suggestion that the sun is not far from an edge. A different parcel waits beyond, and with it a slightly different fit for our bubble. Where our wind leans into that incoming flow, hydrogen piles up into a faint ridge, the hydrogen wall. You cannot see it with your eyes, but far ultraviolet starlight feels it as a subtle extra bite in the Lyman alpha line along nearby sightlines. That absorption, modelled and reobserved for decades, was the first remote sign that our boundary paints a luminous scene where star meets galaxy. More recently, far from the glare of the inner system, New Horizons has swept the sky in Lyman alpha and found a diffuse background brighter than you would expect from scattered sunlight alone. The excess is consistent with a distant contribution from that wall, a ghostly shoreline visible in ultraviolet dusk. You can feel the interstellar magnetic field here as surely as you can feel a swell through a ship's timbers. A small pathfinder, the Interstellar Boundary Explorer, once drew the first all-sky map in energetic neutral atoms and found an elegant surprise, a narrow, bright ribbon draped across the heavens, brightest where our line of sight lies, perpendicular to the local interstellar magnetic field. The feature was not predicted, It was a signpost painted by the galaxy outside. In the years since, theory has offered competing choreographies involving charge exchange and secondary neutrals just beyond the heliopause, but the essence holds our shore is cinched and patterned by the field of the wider sea. This is where the new cartographer matters. The Interstellar Mapping and Acceleration Probe IMAP has now taken its place near the Sun-Earth First Lagrange point, a quiet perch, a little sunward of our world. It launched in late September of the year 2025 and carries 10 instruments, low, mid and ultra-energetic neutral atom imagers to catch the straight-flying messengers from the frontier, telescopes for solar wind and pickup ions to take the pulse of the outflow, a magnetometer to hear the field, a dust experiment, and a diminutive photometer named GLOWS to count far ultraviolet hydrogen light, the helioglow across the sky. IMAP's remit is simple and beautiful to turn particle rain into weather charts for the edge of home. It did not travel alone. Riding the same ascent were two companions bound for that upstream station, NOAA's Space Weather Follow-On Observatory, which keeps an unblinking watch on the solar wind and the sun's outer atmosphere for forecasters, and NASA's Carruthers Geo-Corona Observatory, tasked with charting the vast exosphere of Earth. Together they form a small flotilla, one reading local weather, one mapping the far frontier, one giving context to the thin halo our own planet breathes into space. Poetry about the shore becomes in their company an operational chart. What then will these maps teach us about the waters we are entering? First, they will join outline to waterline shape to pressure. The energetic neutral atom images will trace where the boundary brightens and dims across energies and seasons, while the Lyman alpha glow drawn from the outer system and from GLOWS will mark how strongly the interstellar wind blows and where hydrogen piles into a ridge. The ribbon's slow breathing will be followed like a tide table. Its center and curvature fix the direction of the field beyond, and its brightness tells us how firmly that field is cinching our bubble today. Cross-check those charts with the Voyager's plasma tones outside, and you have the exquisite satisfaction of triangulation. Second, they will test the new geometry of home. For years, we sketched a long comet-like tail, then models that honor magnetic tension and give pickup ions their due proposed, a compact deflated croissant sculpted into twin jets by the field's firm hand. The truth may be a compromise, breathing with the solar cycle and the neighborhood through which we sail. By stacking images across low, mid and ultra energies, each sensitive to a slightly different population, IMAP can decide how stubby or braided the tail truly is and whether the bright arc of the ribbon is painted mainly by those secondary neutrals just beyond the heliopause. Third, they will help us choose our season. The heliosphere thickens with activity and thins with quiet. The galactic drizzle of high-energy particles falls when the sun is busy and rises when the sun is calm. That grand anti-correlation is an old lesson from neutron monitors and spacecraft. What is new is the ability to see, almost in real time, how a pressure pulse near the sun can steepen into a front, sweep the sheath, and be heard months later as a subtle change in the interstellar plasma outside. The inside and the outside are in conversation, and IMAP is designed to translate. And finally, there is the human meaning of all this. We are learning to read the tide on the horizon before we go. New Horizons' soft ultraviolet maps tell us how the gas flows around our neighborhood. The ribbon fixes the direction of the magnetic field pressing on our walls. The Voyager's eavesdropping gives the density just beyond. And IMAP stitches those strands into a living atlas. Out of a handful of photons and a rain of neutral atoms comes the practical knowledge of how to steer through a moving shelter. So let us push a little farther off the beach into the very local interstellar medium proper and follow a single cosmic ray the other way, born in a distant shock threading the galaxy, then feeling the reach of our star's magnetic cloak. In the next part, I want to show how the heliosphere dims and deflects those ancient messengers, why the cycle matters to explorers and instruments alike, and how the first sky maps from IMAP will turn that high-energy weather into something you can plan a journey by. Follow that ancient traveler, then a single galactic cosmic ray born in the aftermath of a distant stellar explosion, tossed into the spiral arms and left to wander. For millions of years, it threads magnetic fields like a tightrope walker on invisible wires, until it approaches the outskirts of our sun's vast magnetic cloak. Here the music changes. The particle meets turbulence, and wandering fields, swirls of irregularity that buffet its path. It scatters, drifts, is decelerated and turned aside as if a hand of wind had cupped gently around it. This slowing and deflection is what physicists call solar modulation, and I love that phrase because it is exactly that our star modulates the harshness of the galaxy, turning volume knobs that rise and fall with its mood. The deep story has been told in careful reviews and models for decades. They show how diffusion, large-scale drifts, convection by the solar wind, and adiabatic cooling inside the expanding flow combine to dim the galactic rain that reaches us. The modulation plays in long, patient time. When the sun is active, sunspots freckling the surface, and the magnetic field wound tight, the cloak thickens and galactic cosmic rays find fewer easy paths inward. When the sun is quiet, the pathways open a little, and the count rises. If you look at the records kept by neutron monitors over many solar cycles, you can see that grand anti-correlation drawn like a tide chart, cosmic ray intensity, cresting near sunspot minima, and ebbing near sunspot maxima. There is nuanced lags of months differences between even and odd cycles, and a dependence on the particle's electric charge sign, but the theme is steadfast. Our bubble breathes and the galaxy's drizzle brightens and dims in time. On faster timescales, the music can break into a sudden hush. When a coronal mass ejection leaves the sun and sweeps past, it carries a turbulent magnetized front that deflects galactic particles for days. Instruments on the ground register this as an abrupt drop called a Forbush decrease, a temporary dimming of the cosmic rain followed by a slow return to normal. For an explorer, these dips are both hazard and help a sign that a shock is near, and a reminder that the sky's background, even when the sun is quiet, is never truly still. All of this would remain abstract were it not for a few beacons holding station across the system. Far beyond the planets, an elderly spacecraft listens to the very local interstellar medium and hears its slow, ringing, faint, persistent plasma tones, whose pitch reveals the electron density of the space just outside our bubble. The finding continuous density measurements in interstellar space was one of those delicate confirmations that feel like poetry turned into data. The hush beyond really does have a different note. Closer in, I picture our new weather station at the Sun-Earth First Lagrange point. The interstellar mapping and acceleration probe arrived after its late September launch, spinning gently like a lighthouse. It measures the outbound wind and magnetic field, while over weeks and months it turns returning energetic neutral atoms into all-sky portraits of the heliosphere's edge. Those portraits, layered across low, mid, and ultra-energy bands, will reveal how pressure pulses and the slow breathing of the solar cycle reshape the frontier through which our cosmic ray walked. Seen beside the long, patient curves from neutron monitors and particle spectrometers, IMAP's particle-made maps should let us translate modulation from theory into daily cartography, where the shield is taut, where it is slack, and how. That will change over the coming season. It helps that IMAP did not travel alone. On the same ascent, NOAA's space weather follow-on Lagrange 1 observatory took its post as a full-time sentinel, watching the solar wind and the corona to feed forecasters with real-time warnings. The small Carruthers Geocorona Observatory joined them to chart Earth's vast exosphere, a translucent veil that is part of the environment our signals and spacecraft must cross. Together, the trio turns the poetry of shore into an operational atlas, local weather, far horizon maps, and context for the halo of our own world. What will that atlas say to our wandering cosmic ray? First, it will show that the heliosphere is not a uniform curtain, but a quilt of varying thickness and temperament. In years when the sun is busy, the large-scale drifts that focus charged particles are suppressed, diffusion becomes rougher, and the overall flux of high-energy visitors at Earth declines. In quieter years, drifts re-emerge, mean free paths lengthen, and the drizzle brightens. Sophisticated measurements from instruments in orbit like the magnetic spectrometers that separate protons from helium and heavier species have even traced charge sign effects and the peculiarities of polarity reversal years when the heavier sun's global field flips and the sky's behavior acquires a strange asymmetry. All of that structure is what IMAP's global portraits will be compared against the shape of the shield, read alongside the changing rain it emits. Second, it will show that short, sharp fronts matter enormously in practice. A single coronal mass ejection racing outward can drive a pronounced Forbush decrease that lasts for days and spans worlds seen at Earth, at Mars, and by spacecraft far downstream. Those events alter the dose an astronaut receives the noise in a detector hunting for faint particles and the steadying rhythm of long-duration flights. With the new Sentinel watching the corona, and interplanetary shocks and IMAP sensing the returning neutral messengers that betray, where pressure has piled up at the border, we can begin to forecast not only flare light and charged particle storms, but the temporary hushes in the galactic rain that follow behind them. And there is the ribbon, that elegant arc first revealed by the Interstellar Boundary Explorer brightest, where our line of sight lies perpendicular to the local interstellar magnetic field. Its slow breathing across energies and seasons is to me a tide table for the whole sky. If the ribbon brightens in certain bands while the sun is quiet, if it shifts subtly as the cycle waxes, we will be reading the pressure of the surrounding sea in real time. Early studies found a near circular symmetry and a stubborn persistence that point to processes just beyond the heliopause. The new maps will test whether secondary neutrals born recharged and born again at the seam do the painting. Either way, the ribbon fixes the direction of the field outside, and therefore the posture our shield must assume. All of this folds back gently to the human scale. For a voyage beyond Earth's magnetic refuge, you can choose to sail nearer the crest of the cycle when the galactic background is lower, but the chance of storms is higher. Or you can favour the trough when the background climbs, but the sun is on average calmer. The neutron monitor's curves, the old Voyager's interstellar tones, the coronagraph's flags, and IMAP's living sky maps can be read together to pick a season and to harden a plan. This is what I love about the modern heliosphere. It has ceased to be wallpaper. It has become weather forecastable, navigable, and in its way kind. In the next part, let me bring that weather to the threshold of worlds. How Earth, Moon and Mars each feel the cycle in their own bones. How detectors and habitats breathe with the rise and fall of the galactic rain. And how the first careful IMAP atlases will teach us to weave quiet corridors through a moving magnetic sea. Back to worlds and the way they breathe with the Sunday. Earth is wrapped first by the heliosphere and then by its own magnetic cocoon, the magnetosphere, which takes the brunt of the gale, reshaping itself as solar weather arrives and trapping charged particles in great toroidal belts. It is not a rigid dome but a living shield, and for life at the surface it turns a cosmic downpour into something more like a drizzle. Step just outside that second cocoon and you feel the difference in your bones, quite literally. On the Moon, where there is no global magnetic field and no substantial atmosphere, a German-Chinese dosimeter on the Chang'e 4 lander measured an average surface dose of roughly 1.4 millisieverts per day, consistent with independent estimates of around 60 microsieverts per hour. The exact number breathes with the cycle, but the lesson is firm: without a sky that holds and a magnet that bends, the galaxy reaches you. Mars sits between these cases, a world with a patchwork of crustal fields and an atmosphere too thin to cushion much. During cruise, the Curiosity rover's radiation assessment detector recorded daily dose equivalents of about 1.8 millisieverts. On the Martian surface, the typical figure falls to about 2/3 of a millisievert per day under quiet conditions. Even that quiet breathes rising and falling with the sun's long rhythm and with passing storms. For crews, this is not an abstraction. It is the number you carry in your pocket while you work. Listen to the sky and you hear the quick weather as well as the slow. A coronal mass ejection plows through interplanetary space, and for a few days galactic particles are deflected. Ground monitors register a sudden dip called a Forbush decrease, and the count recovers slowly as the front passes. We have watched those hushes at Earth for decades, and we have seen them at Mars too, a common physics written across two different shores. Underneath the squalls is the grand tide, the 11-year modulation of galactic cosmic rays by the changing field and flow of the heliosphere. When the sun is active, the cloak thickens and the galactic drizzle dims. When the sun is quiet, pathways open a little and the count rises. Long records show the anti-correlation clearly, with subtle lags and hysteresis from cycle to cycle, a patient handwriting of star and sea. This is why we have at last made the shore into weather. At the Sun-Earth first Lagrange point, a small flotilla now keeps watch. The Interstellar Mapping and Acceleration Probe IMAP launched in late September of 2025 and took its post to convert particle rain into global maps of the heliosphere's edge. On the same ascent rode NOAA's Space Weather Follow-On to provide continuous upstream wind and coronal imagery for forecasters, and NASA's Carruthers Geocorona Observatory to chart Earth's enormous exosphere. Poetry about the shore becomes in their company an operational chart you can steer by. IMAP's toolkit is purpose-built for this translation. 3 energetic neutral atom imagers, IMAP Low, IMAP High and IMAP Ultra, sort the straight-flying messengers by energy, turning weeks and months of counts into all-sky portraits of the frontier. A magnetometer and ion, electron spectrometers take the pulse of the solar wind close to home, while a tiny far ultraviolet photometer called GLOWS reads the faint helioglow in hydrogen's Lyman alpha line. With that suite, the mission can watch the ribbon brighten and fade trace where pressure piles up at the boundary and tie those global changes back to the day-to-day weather felt by spacecraft and crews. Fold this knowledge down to the scale of habitats and detectors, and it becomes surprisingly intimate. At Earth, instruments aboard satellites ride in and out of the Van Allen belts as geomagnetic storms rearrange the trapped populations. At aviation altitude, the background rises and falls with latitude, season, and solar state. On the lunar surface and on Mars, daily dose rates breathe with the sun's long cycle and with each passing front. Choose to voyage nearer the crest of activity, and you can enjoy a lower galactic background at the cost of more frequent squalls. Choose the trough, and you accept a higher drizzle under a calmer Sunday. The physics is settled, the judgment is human. What makes the present moment different is coherence across scales. The voyagers hear a continuous plasma tone beyond the heliopause that tells us the density of the very local interstellar medium. The neutron monitors on the ground sketch the slow swing of galactic counts. The new Sentinel watches the corona and the wind as they launch fronts. An IMAP connects the dots, showing how the frontier itself brightens and dims across energies as the season turns. When the ribbon's arc swells in certain bands, and the ground counts answer with a gentle fall, you can feel almost physically the larger tent tightening. So the field guide becomes a flight plan. Read the cycle by sunspots and by cosmic ray monitors. Watch for forbush dips as a swell before the storm. Fold in the far ultraviolet maps of the helioglow and the annual helium cone to gauge the interstellar wind. Overlay the ribbon's slow breathing to feel how firmly the field outside is cinching our walls. And keep an ear on the Voyager's interstellar chorus for the long tide. Out of those strands, practical windows open quiet corridors through a moving magnetic sea. In the next part, I want to lift our eyes again to the wider neighbourhood and ask what our evolving atlas of shelters, heliosphere, here, astrospheres, there, means for the search for habitable worlds and for the long, careful crossings we will make between them. Lift your gaze from our own tent to the others that glitter across the sky. Every star with breath to spare blows a wind, and every wind inflates a shelter, an astrosphere whose size and texture depend on the star's magnetism, its age, and the weather of the cloud it sails through. We learn to weigh those distant tents in an exquisitely subtle way, by reading an extra byte in the hydrogen Lyman alpha line of nearby stars. That byte is cast by a hydrogen wall, interstellar atoms piled and warmed, where the stellar wind leans into the medium outside and its depth tells us how hard the wind is blowing. It remains even now the primary technique for estimating mass loss from cool stars like our Sun, and with it the reach of their shelters. Once you have a way to weigh the wind, a picture of habitability begins to sharpen. Around small red suns, the M dwarfs that hold most of the galaxy's planets in their keeping, the temper of the wind and the star's flares can be ferocious. The habitable zones of such stars are tucked close in. There, the dynamic pressure of the wind can be thousands of times what Earth feels. The magnetosphere of an Earth-like world can be squeezed inward, and the boundary can pulse dramatically over the course of a single orbit. Models for our nearest neighbour, Proxima Centauri, show pressures of more than 2,000 Earth equivalents and rapid order of magnitude swings in a day. The magnetopore's standoff distance surges and collapses, as if an invisible tide were breathing upon it. That is a neighbourhood where atmospheres must work hard to endure. Push the thought experiment to compact planetary systems like TRAPPIST-1, and the message is the same, perhaps sterner. Simulations suggest dynamic wind pressures of 10 to the 3 to 10 to the 4 times Earth's, implying that only robust fields, thick air, or both can keep the sky in place over geological time. None of this is a verdict against life. The universe is inventive, but it is a counsel of realism. The larger tent drawn by the star matters as much as a planet's own small umbrella. Back to our atlas. If you line up the Lyman alpha astrospheres, the stellar winds that inflate them, and the evolution of those winds with age, you begin to see a choreography. Young stars spin fast, their fields are tangled and strong, and their outflows are vigorous. With time, they lose angular momentum, quieten, and their winds slacken. In that arc lies a shifting radiation climate for the planet's early centuries of storms and glare giving way to calmer millennia. For our Sun and its siblings, this long evolution has been reviewed in patient detail, connecting spin magnetism and wind, a stellar life story told as weather. So where does our new cartographer, the Interstellar Mapping and Acceleration Probe, fit in a tale that seems at first glance to belong to other suns? IMAP's remit is our shore, yes, but the physics is portable. By resolving how our own boundary brightens and dims across energies and seasons, by tracing the famous ribbon that hangs where our sightlines lie perpendicular to the local interstellar magnetic field, IMAP lets us separate the roles of hot, pick-up ions, cooler solar wind ions, and the firm hand of the external field. Those are the same ingredients that sculpt any astrosphere. In that sense, maps of home become templates for distant coasts. An IMAP does not stand alone. On the same September day of 2025, a small flotilla rose from Florida NOAA's Space Weather Follow-on Observatory, bound for the first Lagrange point to provide round-the-clock warnings of solar storms and NASA's Carruthers Geocorona Observatory sent to chart Earth's vast hydrogen halo. Together with IMAP's global portraits of the frontier, they turn poetry about the shore into an operational chart, local weather, far horizon, pressure, and context for the enormous veil our own planet breathes into space. The ribbon itself remains one of my favorite signposts. First revealed by the Little Ibex mission more than a decade ago, it is a bright arc and energetic neutral atom, light draped across the sky, where the field beyond runs sideways to our view. Its persistence over years, its nearly circular symmetry, and its slow breathing with the cycle told us elegantly that the galactic magnetic field cinches our walls. IMAP's finer energy steps and broader dynamic range will interrogate that signpost season by season, testing whether secondary neutrals, born recharged and born again, just beyond the heliopause, are doing most of the painting. Either way, the ribbon is a tide table for the whole tent. What do these shelters mean for crossings, for the long, careful passages we dream of making between the tents of stars? First, they tell us there are safer seasons. The galactic drizzle of high-energy particles dims near the crest of the sun's cycle and brightens in the troughs. That old anti-correlation is written into the records of neutron monitors and missions alike. Second, they tell us to read the fronts. A single coronal mass ejection can carve a temporary hush in the galactic rain, a Forbush decrease even as it raises the immediate storm risk. With SWFO at Lagrange 1 watching the corona and wind in real time, Carruthers giving us a context image of the geocorona's great halo, and IMAP returning the far frontier maps, we can pick windows, quiet corridors through a moving magnetic sea. Third, our shore teaches us to look outward with the right questions. When we point a space telescope at a nearby cool star and see a Lyman alpha line nibbled by its hydrogen wall, we are not just measuring mass loss, we are inferring radiation climate for any worlds tucked within. When magnetohydrodynamic models of Proxima's wind predict thousands-fold pressures and whipping magnetopauses, we are tasting the lived weather of an exo-Earth. And when a future mission maps energetic neutrals around another star, an audacious step but not unthinkable, the grammar we learned here will let us read that map. There is a gentler lesson too. The local bubble that cradles us, a cavity likely carved by ancient supernovae, shapes the interstellar wind that presses on our wall. Within it, the local interstellar cloud sets today's pressure and field. Beyond it lies another parcel with a slightly different fit for our cocoon. As IMAP stacks seasons of images and as New Horizons continues to sweep the sky in Lyman Alpha from far beyond the giants, we will be able to tell not only where the shoreline lies, but also how the wider sea is flowing. Navigation becomes geography, so the search for habitable worlds and the plotting of passages between them fold back into a single craft, the reading of shelters. We weigh winds by their hydrogen walls. We watch ribbons for the pull of the galaxy outside, and we time our crossings by the slow breathing of a star. The next step is to take this field guide and walk it to the threshold of interstellar flight, to ask how a ship and its crew might live in the heliosheath for years, what the Voyagers have already taught us about the music beyond the gate, and how IMAP's first atlases will refine the path. In the part to come, let's sketch that outward journey. In practical terms, life support beneath a changing drizzle, radiation to symmetry, in a breathing tent, and the quiet art of choosing when to leave home. Take the field guide and set it gently beside the life of a crew. In deep space, the dosimeter becomes a kind of compass. It tells you how hard the galaxy is knocking. On the moon, without a global magnetic field or the kindness of a thick sky, instruments have measured an average surface dose, a little under 1.5 millisieverts per day, a figure that rises and falls with the sun's mood. On Mars, the Curiosity rover's detector found a typical surface dose a shade under 2/3 of a millisievert per day under quiet conditions, while the cruise through interplanetary space ran close to 2 millisieverts per day. Those numbers give shape to the air you do not breathe out there. They are the texture of the invisible weather through which a ship must pass. So you choose your season. Across the long rhythm of the solar cycle, the galactic drizzle of high-energy particles falls as the sun grows busy and rises as it quietens. It is the old, graceful anti-correlation written in decades of neutron monitor records. Lay that tide alongside the quicker squalls, the sudden outbursts that ride with flares and coronal mass ejections, and the trade becomes plain. Sail nearer the crest of activity, and you enjoy a lower background of cosmic rays while accepting a greater chance of storms and their turbulent fronts. Sail in the trough and you live with a higher drizzle under a calmer Sunday. It is not a trick of poetry, it is measured physics, and it is the beginning of prudence. Those fronts have a signature you can feel in the data. When a coronal mass ejection's magnetic sheath washes over a world, galactic particles are deflected for days. On Earth ground, instruments register a sudden dip known as a Forbush decrease. At Mars, Curiosity's detector and the Maven orbiter see the same hush arrive a little later, the same physics written across two different shores. These dips are both hazard and help warning buoys that say a shock is near, and reminders that even a quiet sky is alive with weather. Upstream of all this, a small flotilla now keeps watch where the Earth-Sun gravities balance. The interstellar mapping and acceleration probe IMAP took its place near the first Lagrange point, a quiet perch, a little sunward of home in late September of the year 2025. Its remit is as simple as it is beautiful to turn a rain of returning neutral atoms into living maps of the heliosphere's edge, while sampling the breath of the solar wind as it flows past. On the same ascent rode NOAA's Space Weather Follow-On Observatory, set to provide round-the-clock upstream solar wind and coronal imagery for forecasters, and NASA's Carruthers GeoCorona Observatory, built to chart the vast hydrogen halo that our own planet breathes into space. Poetry about the shore becomes in their company an operational chart. IMAP's toolkit is a craftsman's cabinet. Low, high, and ultra-energy neutral atom images catch the straight-flying messengers born where our wind meets the interstellar flow. Ion and electron telescopes take the pulse of the local plasma. A magnetometer listens to the field's soft turns, and a small far ultraviolet photometer nicknamed GLOWS reads the faint helioglow in hydrogen's Lyman alpha line. 10 instruments, one purpose: to watch the fabric of the sun's bubble tighten and slacken with season and storm, and to show travelers where the pressure ridge lies today. The long horizon is anchored by two very old beacons. Beyond the heliopause, that wavering contact between our wind and the sea outside, one of the voyagers has been listening to a continuous narrow chorus in the interstellar plasma. The pitch of that song gives the electron density out there and shows it rising and falling gently across the years. It was among the clearest signs that we had truly stepped beyond the sun's long exhalation. When a great pressure pulse leaves the sun and sweeps the outer system, that interstellar tone can shift, telling us that inside and outside are in conversation. Lay these strands together and a practical cadence emerges for a crew. Each morning you would read the Space Weather Sentinel's stream solar wind speed, density and field, coronagraph images of any fronts that have lifted off the Sunday. You would compare that near-term weather with IMAP's slowly accumulating portraits of the frontier, where the ribbon of returning neutral atoms brightens where the edge seems taut or slack in different energy bands. You would fold in the far ultraviolet maps of Earth's great halo from Carruthers, because even the exosphere is part of the environment your ship must cross. And you would bind it all to the long tide traced by the Voyager's interstellar tones. Out of those disparate whispers comes a sea state for the week ahead. Radiation planning sits on top of that sea state like a quiet arithmetic. You temper the steady galactic background with shielding and with time days in a storm cellar when the sun snarls weeks of outward work, when the sky is more forgiving. You watch for the hushes that Forbush decreases bring, because they alter both hazard and opportunity. And you remember the scale of the journey. Even a round trip to Mars in the simple capsules we imagine today would carry cumulative doses that press against the limits of comfort and caution. The art is in smoothing the peaks without inviting worse. There is one more layer of grace in IMAP's remit that speaks to voyaging far beyond Mars. Its energetic neutral atom cameras do not simply draw a coastline, they sort the frontier by energy, which is to say by depth. The higher energy messengers carry news from slightly different places and pressures than the lower energy ones. Stack those layers, and you begin to see not only where the shore lies, but how thick it is, how it breathes from month to month, and where a long-duration craft might find the quietest corridors through the heliosheath. That is a new kind of navigation, and it is being written in patient sweeps from a million miles sunward of us. And always beneath the engineering, there is the human rhythm of the ship itself. The quiet voice reads out the day's forecast. The dosimeter ticks like rain on a window, The magnetometer hums a little deeper when a front slips by. In such small sounds, a crew learns to live with a sky that moves. In the next part, I want to carry that rhythm outwards, still further to the long years in the heliosheath, where pickup ions hold the pressure and the music of turbulence changes key, and to ask how we might design a passage that is not merely survivable but gentler line across the sun's changing sea, that respects both the physics and the people who must journey on it. Out there in the long years of the heliosheath, the music settles into a lower, restless key. I picture the hull humming softly as the sun's river, slowed and warmed, begins to negotiate with the sea beyond. What the old data teach and what we must design around is almost cheeky in its inversion. The particles that did not begin here now run the show here. Neutral atoms from the galaxy wander inward. Sunlight or collisions ionize them, and the newborn pickup ions are seized by the wind's magnetic field and flung along for the ride. By the time you reach this buffer, those pickup ions hold most of the thermodynamic budget, soaking up the energy lost at the termination shock and providing the pressure that pushes back on the interstellar medium. That is not a poet's flourish, it is the working physics of the outer wind. This matters for a passage because pressure carriers set the weather. In early sketches, we imagined a single engine forging so-called anomalous cosmic rays at the shock like sparks from a grindstone. The voyagers gently corrected us intensities built downstream, not right at the shock, implying many small theatres of acceleration rather than one grand stage, stochastic processes in the sheath geometry. Along the flanks, pulses that come and go as the boundary flexes. If you are threading a crew through that hinterland, you are not planning for a cliff, you are planning for a rolling factory floor. Listen and you can hear the room you are in. The magnetic field in the sheath flickers with compressive and non-compressive turbulence. The spectrum hints at cascades and intermittency driven in part by the very pickup ions that now dominate the energy budget. Because the flow is subsonic here, even our usual trick of converting time into space must be handled with care. This is a four-dimensional medium. The practical lesson is clear enough: you smooth your days with redundancy and patience, because the field will not hold still under your hand. Design then becomes choreography. I would ask IMAP, our lighthouse, a little sunward of Earth, to keep handing us layered portraits of the frontier, energy by energy, season by season. Energetic neutral atoms born where ions steal electrons at the boundary, fly straight, free of magnetic fields, and our cameras count them. High-energy messengers tend to carry news from slightly different places and pressures than low-energy ones. So when you stack those images, you begin to see not only where the shoreline lies, but how thick it is, where the pressure ridges sit today, and how the fabric is breathing. That is how you sketch gentle corridors through a living coast. The ribbon is my favorite tide table. Years ago, Ibex drew a luminous arc in neutral atom light brightest, where our line of sight lies perpendicular to the local interstellar magnetic field, and told us elegantly that the galaxy outside cinches our walls. IMAP's finer energy steps and wider dynamic range now interrogate that signpost. If the arc brightens in certain bands while the sun is quiet, if its curvature shifts as the cycle waxes, then we are watching the external field tighten or relax the tent in real time. Season your route to that breathing, and the ship will feel it as a little less weather in the bones. And the coastline itself, do not commit to the old comet's tail unless the sky insists. Models that honor magnetic tension and give pickup ions their due favor. A compact deflated croissant with twin jets that fold back the field's firm hand shaping the pastry. For a pilot, that means shorter, stubbier downstream structure, less of a single endless wake and more of a braided plume. In practice, you treat tail and flanks as variable terrain, and you let the maps, not the metaphors, choose your lane. Ahead of the prow, forget the crashing bow shock of textbook artists. The sun's motion through the local cloud is gentle, and the external magnetic field is firm. What forms is a broad bow wave, a pressure ridge rather than a breaker. That revision is not trivial. A wave means fewer violent surprises at the nose, and a boundary that negotiates, not smashes. It is a quieter sea to cross if you have the patience to read it. None of this replaces the beacons outside. Beyond the heliopause, the voyagers hear a continuous narrow chorus in the interstellar plasma, its pitch giving the electron density of the very local sea. When great pressure pulses leave the sun and roll outward, that interstellar tone can shift months later. Pair those sounds with IMAP's evolving sky maps, and you have triangulation of the best kind: inside breath, outside reply, and the middle distance pictured in particles. Even as instruments are husbanded for power in their fifth decade, the reference tracks endure. So how to make the crossing gentle first travel with the stars long tide at your back? The grand anti-correlation is an old one. galactic cosmic rays dim near the crest of activity and brighten in the troughs. For deep voyages, you may favour the crest to trim the drizzle, accepting a greater chance of squalls from solar outbursts, and you harden your plan against those fronts. Second, use the hush itself. When a coronal mass ejection throws a turbulent sheath through the system, neutron monitors record a 4-bush decrease, and detectors at Mars do as well. Dose rates dip for days. That is hazard, but it is also breathing space if you are already sheltered. Third, steer by the ribbon and the helioglow. If the neutral atom arc is taut and the far ultraviolet hydrogen glow bright beyond the giants, the outside is pressing firmly and your corridors will be narrower. Finally, accept that home is still being redrawn. IMAP's 10 instrument cabinet, IMAP low and IMAP high, and IMAP ultra for the neutrals, spectrometers for solar wind and pickup ions. The magnetometer, the small photometer called GLOWS, was built precisely to separate who is doing what at the seam between winds. As those layers accumulate, we will know whether secondary neutrals beyond the heliopause we do most of the painting, how pickup ions shoulder the pressure differently with the cycle, and where the crescent pinches or relaxes. The better the atlas, the kinder the line we can set for cruise. There is solace in the continuity. Parker's solar probe keeps reporting from the headwaters switchbacks and jets flicking the wind into being, while IMAP paints the mouth, and the voyagers keep an ear on the sea outside, Birth frontier beyond. It is the same river heard in 3 registers, and it tells us we can treat the heliosphere as weather rather than wallpaper. In the next part, I want to lift us from the chart table to the bridge and look outward once more to the long, careful step past the heliopause, where interstellar weather becomes the daily sky, and to the human question that has threaded this talk from the start, what it means in practical and tender terms to call a magnetic bubble home while we learn to leave it. Step with me across that wavering line, where the sun's breath thins and the galaxy's weather becomes the daily sky. Out here, the hush has a pitch. When the first of the voyagers drifted beyond the heliopause, its plasma wave antenna began to hear a persistent narrow whistle, the natural ring of interstellar electrons. Turn tone into density, and you find a space that is far denser than the outer solar wind, yet still almost inconceivably thin, only a few hundredths of a particle in each cubic centimeter, and crucially alive with gentle compressions that rise and fall over months and years. That continuous hum, discovered years after the initial shock-triggered bursts, gave us our first steadily sampled barometer of the very local interstellar sea. Cosmic rays speak with a different accent beyond the wall. As Voyager 1 stepped into interstellar space in late August of the year 2012, the flux of low-energy ions from inside our bubble collapsed, and the true galactic population surged to levels not seen since the spacecraft's youth. In the months that followed, the mission's charged particle instruments traced the new normal higher galactic intensities, odd anisotropies, and a pitch angle story that reminded us the local magnetic field and turbulence matter every bit as much as raw distance from the Sunday. The heliopause, it turned out, is not a hard border. It is a membrane that filters and redirects. Name the sea and the coast becomes legible. We sail through the local bubble, 1,000 light-year-wide cavern carved by ancient supernovae, whose expanding shell now hosts most of the star-forming clouds near the Sunday. Within that cavern, the local interstellar cloud, warm Apache threaded by a modest magnetic field, sets today's pressure and flow at our boundary. It is a beautiful chain of cause and effect explosions long past, hollowed a cavity. Its walls gathered the gas that became young stars, and we tucked inside, feel the cavity's pressure on the heliosphere now. The field beyond writes its signature on our sky. A small, elegant mission called the Interstellar Boundary Explorer revealed a narrow, bright ribbon of energetic neutral atoms, an arc draped across the heavens, brightest where our line of sight lies perpendicular to the local interstellar magnetic field. It was not predicted. It told us with a cartographer's economy that the galaxy's field cinches and patterns our walls. A decade of maps showed the ribbon breathing with the solar cycle, an external tide table for our internal weather. Even the shape of home had to be relearned. Where we once drew a long comet-like tail, modern models that honour magnetic tension and the power of pickup ions propose a compact, deflated croissant figure with twin jets drawn back by the field's firm hand. And up front, the shock once sketched in textbooks has softened to a broad bow wave. Our sun's motion through the local cloud is too gentle and the external field too strong to form a roaring breaker. The coast is quieter, more negotiated than we imagined. There is weather here too slow, dignified and real. Voyager's plasma wave ear hears the interstellar density slide upward and down in graceful undulations. At the same time, its cosmic ray counters register subtle reorganizations in direction and intensity as turbulence and field lines rearrange. The picture that emerges is not of a static ether, but of a living medium into which our star exhales. Even the absence of shock at the bow becomes meaningful. A wave, not a breaker, means the horizon changes in shades, not steps. Dust adds a grainier note to the score. Far beyond Neptune, New Horizons has flown a long transect with a student-built dust counter and found a higher than expected flux of impacts as it approached 60 astronomical units, news that complicates our picture of the sombre outer reservoir of grains and for shipwrights adds a practical line to the checklist for hull and sail. Even in a sea as thin as this, a steady patter of motes matters over years, and back toward the sun, new cartographers have taken their posts. In late September of the year 2025, the Interstellar Mapping and Acceleration Probe, seated near the first Lagrange point, launched with a cabinet of 10 instruments to turn returning neutral atoms into global portraits of our frontier, while companion craft from NOAA and NASA watch the solar wind and the Earth's enormous hydrogen halo. With those eyes, shore becomes operational. We can see how pressure piles into a ridge, how the ribbon brightens and fades, how the field outside tightens or relaxes the tent with the season. Even the ultraviolet dusk is beginning to give up its secrets. New Horizons has swept the sky in hydrogen's Lyman alpha light from more than 50 astronomical units and found a diffuse background brighter and smoother than many models foretold, evidence perhaps that the local hot bubble's bright. Young stars are lighting the cavity's walls, and that resonant scattering is amplifying a galactic glow. It is a gentle reminder that the shoreline's hydrogen wall, seen toward nearby stars as an extra bite in their Lyman alpha lines, is part of a larger conversation between our tent and the wider room. What does all this mean for travelers who would dwell beyond the gate? It means a calendar and a compass. The calendar is the sun's own cycle. Near the crest, the galactic drizzle dims, but storms grow more likely. Near the trough, the drizzle rises under a calmer star. The compass is a living atlas, Voyager's interstellar tones for local density cosmic ray counters, for the background ray neutral atom portraits for where the wall is taut, and ultraviolet maps for the glow of the wider sea. Read together, they offer not certainty but kindness, a way to choose quieter corridors through a moving medium and to know in advance the texture of the days. In the next part, I want to bring that atlas down to the size of a ship and a crew, how you live with the hum and the drizzle and the dust, how shielding, timing and simple ritual make a gentler passage, and how, even as we learn to leave this magnetic cocoon, we carry its music with us like a homeward note. Bring the atlas down to the size of a ship and to the pulse of a crew. Each morning I would stand in the hush of the cabin and read the sky. As sailors have always done, only our sky is made of charged particles and faint ultraviolet. Upstream, near the first Lagrange point, the Interstellar Mapping and Acceleration Probe, 10 instruments, strong spins like a lighthouse and turns the rain of returning neutral atoms into living maps of the heliosphere's edge. Alongside it, the Space Weather Follow-on Observatory keeps around-the-clock watch on the solar wind and the sun's outer atmosphere for forecasters, while the Carruthers Geocorona Observatory eyes the Earth's far-flung hydrogen halo. Together they make shore into weather, a barometer for the frontier, a nowcast of the wind and context for the veil our own world breathes into space. Life out here is choreographed around dose as much as distance. We know the texture of the ambient rain because we have measured it on the Moon instruments, recorded an average surface dose a little above 1 1/3 millisieverts per day. On Mars, the rover's detector typically finds about 2/3 of a millisievert per day under quiet skies, while the cruise through interplanetary space tends toward roughly 2 millisieverts per day. These are not abstract units. They are the weather in your bones, rising and falling with the sun's long rhythm and each passing front. So we time our days to the star. Near the crest of activity, the grand tide runs in our favour. The galactic drizzle is thinned by the heliosphere's wound-tight field and bustling wind. In the trough, the drizzle rises under a calmer Sunday. The choice for travellers is a humane one, not just a technical one. Sail nearer the crest and harden the plan against squalls, or favour the trough and live with a steadier, higher background. Either way, the rule of thumb is written in decades of records and refined now by the mapping probe's fresh view. And then there are the quick weathers, the hushes that arrive after a front. When a coronal mass ejection pushes a magnetised sheath across a world, galactic particles are briefly turned aside. On Earth, neutron monitors call it a 4-bush decrease. At Mars, the same dip has been seen on the surface by the rover and in orbit by the Maven spacecraft. For crews, those dips are both a warning buoy and a small courtesy evidence that a shock is near, and a reminder that even a quiet sky breathes. Shelter is a craft as old as boats. In deep space, the simplest, kindest physics is that light, hydrogen-rich matter makes better armor against the roving ions than heavy metal. Water polyethylene and other low-Z materials soften the blow without spawning as much harmful fragment spray as aluminium. We design around that truth place tanks where they thicken the hull, line a small inner room to serve as a storm closet, even consider water-filled garments that can be donned in a hurry when a solar event is inbound. The engineering literature and agency guidance converge on the same themes: centimeters of water equivalent for the worst solar storms, careful layout of supplies and tanks, and humility about what shielding can truly do against the deepest galactic rain. There is comfort in specifics. Designs for storm shelters intended to be made ready in less than an hour, and to hold a crew through a day or two, can be strengthened simply by rearranging what you already carry: drinking water, food, soft goods, anything rich in hydrogen. Recent guidance suggests on the order of 10 centimeters of water, equivalent to ride out a once-in-a-millennium solar particle event. Double that to hedge even further. It is pragmatic, almost domestic stack, the bags where human bodies will be, and it turns physics into furniture. Outside, our beacons keep time. Far beyond the gate, the old Voyager hears a continuous narrow tone in the interstellar plasma. From its pitch, we read the density of the thin sea beyond. That hum rises and falls gently across the years, and when a great pressure pulse leaves the sun and rolls outward, the tone can shift months later. Read alongside the mapping probe's portraits of the frontier, and the Space Weather Sentry's real-time wind that distant ear lets us make a chart with inside breath and outside reply, and a picture in between. If you like checklists, most crews do, ours might run like this. First, read the slow tide by sunspots and by the long patient curves from cosmic ray monitors. Second, watch for fronts and their hushes, four-bush dips which mark the passing of a shock and offer sometimes a brief lull in the drizzle. Third, pull down the latest frontier maps from the mapping probe low, mid and ultra energy bands, because the edge is layered in depth, and a brighter arc at certain energies can mean a tighter, thinner fabric where we plan to work. Fourth, take the Sunward Sentry's continuous streams, solar wind, speed, density, temperature field, and feed it to the human calendar: engine burns, spacewalks, surveys. Fifth, glance at the exosphere images, fresh frames of the geocorona, because even the Earth's halo modulates the environment that ships must cross. It is a ritual more than a routine, and rituals steady the hand. The instruments themselves deserve their own quiet reverence. The mapping probe's cabinet spans the spectrum of messengers, low, mid, and ultra-energy neutral atom imagers to paint the far coastline. Telescopes to count the solar wind and the pickup ions that dominate the pressure in the outer river. A magnetometer to hear the field. A dust and interstellar atom experiment. And a small photometer glows to read the faint helioglow in hydrogen's Lyman alpha light. They are all tuned to a single question: how does a star build a refuge for its worlds, and how does that refuge breathe? What I love most, though, is that the physics collapses back into something human. A water bag moved from one locker to another is a better night's sleep. A forenoon spacewalk shifted to the next orbit becomes a wiser stroll. A little room lined in softness and patience is a hearth when the sun snarls. And over the months, as the mapping probe's maps thicken and the Voyager's hum continues beyond the wall, the idea of home expands to include the space between worlds, the long magnetic shoreline that has always held us. In the next part, let's step out of the cabin and onto that shore itself, slowly, tenderly, to look at the hydrogen glow, the bright ribbon painted by the galaxy's field, and the changing fit of our bubble as the new cartographer sends back its first full sky portraits. Step with me gently onto the shore itself. If you adapt your imagination, you can almost see it, a faint, pearly wash across the sky, where neutral hydrogen atoms scatter the sun's ultraviolet heartbeat. We call it the hydrogen glow. From far beyond the giants, the New Horizons spacecraft has taken long, unblinking looks at that glow, with its ALICE spectrograph sweeping the heavens in the Lyman alpha line. In late summer of the year 2023, when the craft was nearly 57 astronomical units from the sun, the team stitched together the first deep all-sky maps from that vantage. What they found was not a cluttered shoreline, but a surprisingly uniform, bright background, consistent with a gentle illumination from the walls of the local bubble around us, lit by hot young stars and then amplified by resonant scattering in the thin gas. It is a picture in which the familiar hydrogen wall at the heliosphere's edge exists, but the broader ultraviolet dusk is painted by the neighborhood itself. That is a beautiful thing to hold in mind as we look outward our coast and the room it is in glowing together. The hydrogen wall is a quieter phrase than it sounds. Where the sun's wind leans into the very local interstellar flow, neutral hydrogen atoms pile up and warm into a gentle ridge. We do not see it with human eyes. We infer it as a subtle red-shifted bite in the Lyman alpha line of nearby stars, an extra absorption component first teased out in the 1990s and patiently modelled ever since. It was the earliest remote sign that our bubble imprints a seam on the galaxy just outside, and that seam's depth becomes a barometer for the pressure our environment exerts on us now. In that sense, the hydrogen wall is both geography and weather report, a place and a gauge at once. But the shoreline does more than dim a line in starlight. It throws messengers back toward us. At the frontier, fast-charged particles swap electrons with neutral atoms and become energetic neutral atoms, straight-flying couriers that ignore magnetic fields and cross the void as if on rails. A small pathfinder, called the Interstellar Boundary Explorer, turned those couriers into a global portrait of our edge and revealed a surprise. A narrow, luminous arc draped across the sky, brightest where our lines of sight are perpendicular to the direction of the magnetic field outside. We learned to call it the ribbon. It told us simply elegantly that the interstellar magnetic field is not a distant abstraction. It cinches the walls of our shelter and leaves its mark in neutral light. Over the years that followed, the ribbon's persistence, its near circular symmetry, and its slow breathing with the solar cycle became a tide table we could actually read. Where the arc-brightened pressure was piling in the outer reaches, where it dimmed, the cinch had loosened. The precise choreography is still being debated. Secondary neutrals born just beyond the heliopore's retention regions in the very local interstellar medium. And other subtle dances have all been proposed, but the central lesson holds the galaxy's magnetic field shapes our border in real time. For a civilization that intends to travel, that is not poetry, it is forecast. This is where our new cartographer, interstellar mapping and acceleration probe, comes into its own. Seated near the first Earth-Sun Lagrange point, a quiet perch a little sunward of home, the observatory launched in late September of the year 2025 with a cabinet of 10 instruments designed to unpick frontier by energy, by species and by season. 3 energetic neutral atom images span low, middle and ultra-high energies so that the maps are not just pictures but layers. Telescopes for ions and electrons read the outbound wind and the pickup ions that dominate the outer river's pressure. A magnetometer listens to the interplanetary field. A compact dual-ion composition experiment weighs the ingredients. A dust collector tastes the grains drifting through. And a tiny, far ultraviolet photometer, aptly named Global Solar Wind Structure, counts the helioglow itself, the same hydrogen dusk. New horizons mapped from the deep, but now watched steadily from near Earth. Taken together, the suite is a translator between inside and out. IMAP did not travel alone. Riding the same ascent were 2 companions meant to anchor the near-term weather, the space weather follow-on observatory at the first Lagrange point, the National Oceanic and Atmospheric Administrations round the clock, Sentinel for the solar wind and the sun's outer atmosphere, and the Carruthers Geocorona Observatory, built to image the Earth's enormous hydrogen halo, the geocorona that every departing signal and spacecraft must cross. 3 instruments, 1 rocket, 1 purpose, to turn shore into an operational chart. With that flotilla on station, we can begin to read the shore the way mariners read a tide rip. Energetic neutral atom portraits tell us where the boundary is bright and taut. Magnetometer and ion sensors near Earth recount the state of the outgoing wind. Ultraviolet photometry of the helioglow shows how interstellar hydrogen is threading through the system today. And far beyond Voyager's plasma wave ear, still hears a narrow, persistent hum that reveals how dense the interstellar sea is just outside the gate. When those strands are woven, when a pressure front lifts from the sun, when the ribbon brightens in certain energies, and when the interstellar tone rises months later, we are not guessing. We are triangulating the temperament of a living border. Even the overall posture of home is being redrawn in this language. For decades, we sketched the heliosphere as a long, comet-tailed wake. Then models that honor magnetic tension and the muscle of pickup ions taught us to see a more compact figure, something like a deflated croissant with twin jets folded back by the sun's field. Upstream, the crash of a bow shock has softened into a broad bow wave. Our motion through the local cloud is gentle, the external field firm. The coast, in other words, is negotiated rather than battered into shape. IMAP's layered maps are built to test exactly that kind of shape-shifting, how the croissant pinches and relaxes with the cycle, and how the bow wave brightens when the medium leans harder upon us. There is something quietly moving about the way all these signs agree. A faint, nearly uniform Lyman alpha dusk says the room around us is glowing. An ancient technique measuring the tiny extra byte in stellar Lyman alpha still weighs the ridge at our border. A ribbon of energetic neutrals tells us the external magnetic field's direction and its insistence. An upstream sentry turns those hints into daily cartography, and a craft beyond the gate listens to the sea itself. We begin to treat the heliosphere as weather, not wallpaper. A fabric that thickens and slackens, a coastline that breathes a shelter, that remembers the touch of the galaxy's hand. And if you ask what this means in the human voice rather than the technical one, I think it is this. Before we cross to interstellar space, we must understand the shore. The patience to read a diffuse glow, to weigh a line in starlight, to follow a ribbon across seasons. These are not academic curiosities. They are the kindnesses that make voyages gentler. In the next part, I want to stand with our imagined crew at the rail and watch the first long sequences from the mapping probe settle into place. Energies layered like rain bands on a radar image, and ask how we turn those portraits into a calendar you can live by, which months to favor, which lanes to thread, and how the galaxy's quiet pressure writes itself into the rhythm of a ship. I find myself imagining the first trickle of maps from a new cartographer, quiet sheets of color, unrolled in a darkened room. Because to make sense of a frontier, you do not rush to the edge, you learn its seasons. Since late September of the year 2025, the Interstellar Mapping and Acceleration Probe has been coasting toward the first Sun-Earth balancing point. That subtle perch, a little under 1.5 million kilometers sunward of our world. It rode a Falcon 9 from Launch Complex 39A at the Kennedy Space Center on Wednesday, the 24th of September, just after 7:30 in Eastern morning light, alongside two companions, the Carruthers Geo Corona Observatory and NOAA's Space Weather Follow-on at Lagrange 1. That launch was more than spectacle. It was a promise that we would begin to keep time with our star's great bubble, not as a single picture, but as a calendar written in particles and light. IMAP carries 10 instruments, but 3 give us the long, slow heartbeat of the heliosphere in a particularly elegant way. Imagine 3 overlapping cameras for atoms rather than photons, IMAP low, IMAP high, and IMAP ultra, each sensitive to a different band of energy. The lowest energy imager, IMAP low, gathers atoms that have been stripped of their charges and set free as neutral messengers at energies below roughly 2 kilo-electron volts. It sits on a pivot like a patient lighthouse, so that across the months it can sweep nearly the whole sky. IMAP high listens a little higher, from about 0.4 to about 15.5 kilo-electron volts in 2 identical heads, tilted 45 and 90 degrees to the spacecraft's spin axis, knitting almost the entire celestial sphere into its view. And IMAP Ultra, a matched pair opposite one another on the observatory, extends the melody upward across roughly 3 to 300 kilo-electron volts, resolving the brisker notes from the heliosphere's boundary. Together like a trio of string instruments tuned to different registers, they can render the same theme, our magnetic shoreline, in harmonies of energy. Because these are neutral atoms, they travel in straight lines. Charged particles are braided into magnetic fields and must follow their twists. Neutrals ignore the knots and go arrow true. That is why the mission will, over weeks and months, draw global maps of the boundary without ever leaving the inner solar system. It is cartography by messenger, a discipline pioneered by an earlier spacecraft called IBEX, which surprised us in the year 2009 by revealing a narrow, almost circular ribbon of enhanced atom flux draped across the sky. The prevailing view today is that this ribbon arises from secondary neutral atoms. Ions that left the heliosphere were turned back and re-neutralized in a sheath of interstellar gas and magnetic field, and then came straight back at us, along lines of sight where the interstellar magnetic field points sideways to our gaze. IMAP's 3 images are built to test this picture with far finer detail and to watch the ribbon breathe with the solar cycle. Yet atoms are not the only clock hands we will follow. There is a 4th instrument I love for its simplicity and poetry. It is called GLOWS, the Global Solar Wind Structure Instrument, and it does not make pictures in the usual sense. Instead, it counts photons at the precise wavelength of hydrogen's Lyman alpha line as the spacecraft spins a single pixel photometer, clicking softly like rain on a tent. Those clicks trace an all-sky ultraviolet helioglow formed when a river of neutral hydrogen from interstellar space wanders into our neighborhood, absorbs sunlight at that specific wavelength and re-emits it. About 1,000 such photons per second will patter into glows, and their pattern is a weather map of hydrogen itself, brighter where the river thickens, dimmer where it thins, modulated as the solar wind waxes and wanes over the 11-year rhythm of sunspots. And there is a second ultraviolet chronicle unfolding even closer to home. The Carruthers Geocorona Observatory, named for George Carruthers, whose far ultraviolet camera flew to the moon with Apollo 16, now rides the same gravitational perch, Lagrange 1, that turns its eyes back toward the Earth to watch. Our exosphere, the delicate hydrogen halo that stretches far beyond the familiar blue of the lower sky. Two far ultraviolet imagers will study how that halo swells and ripples with seasons and storms thrown from the sunday. For the first time, we will not be guessing the edge of our own atmosphere. We will watch its luminous crown evolve day after day, in context with everything else IMAP and its neighbours see. Those neighbours include NOAA's Space Weather Follow-On Observatory, an operational sentinel that complements IMAP's research with continuous monitoring. It carries, among other instruments, a compact coronagraph to image coronal mass ejections, a solar wind plasma sensor, a suprathermal ion sensor, and a magnetometer. Its timeline is a parable of patients' arrival at the Lagrange 1 point around January of the year 2026, commissioning through mid-year, and then like a lighthouse keeper settling into the long night, 24-hour-a-day service feeding real-time data to forecasters. When the sun hurls a storm, we will trace it in the coronagraph sweep, sample it in the plasma, feel it in the field, and in parallel watch the geocorona flare and the helioglow shift. The shore, the weather, and the wider ocean will be on the same page of the same calendar. If you listen beyond the inner system, if you lean out, as it were, over the rail, you can already hear what lies outside. Voyager 1 has recorded a faint, persistent song in the very local interstellar gas narrowband plasma waves that hum along, revealing the density of the medium beyond the heliopause. It is as if, past our surf, there is a steady swell we can read as sound. That hum, continuous since about the year 2017, is another metronome by which to keep the months of the heliospheres breathing. Farther still, the New Horizons spacecraft, now tens of astronomical units from the Sun, used its ultraviolet spectrograph in September of the year 2023 to map diffuse Lyman alpha light over most of the sky. The brightness it found remarkably uniform, and on the order of a few dozen Rayleigh, suggests that hot stars may be washing the inner walls of the local hot bubble with ionizing light, which then recombines and scatters. Even our bubble's neighborhood shines, even the void has weather. IMAP's helioglow counts will fold into that story, linking local variations to this broader glow painted across the sky. So the why now is clear. With IMAP's Atom Maps Glows photon rain, Carruthers' Earth Crown portraits, and NOAA's Steadfast Sentinel, we can place cosmic rays, the high-energy wanderers that shape habitability in their proper seasons. We have known for decades that bursts of solar activity can briefly suppress the galactic rain of cosmic rays, an effect called a forebush. Decrease seen in neutron monitors on Earth and even by instruments riding the Martian surface and the Maven orbiter above. But now we can associate each dip not merely with a passing storm, but with the great geometry of the bubble itself. We can knit an almanac of radiation, a practical ephemeris for life and exploration. And that is where I want to take you next, to lay out gently and clearly how these portraits become a calendar, how often the maps are refreshed, how the energy bands layer like isobars on a weather chart, how long it takes a coronal event to ripple through the ribbon's light, and when the quietest windows arrive for journeys outward. Let us turn the pages together. So let us at last turn the calendar over and see how the shoreline keeps its time. At the first Sun-Earth balancing point, the Interstellar Mapping and Acceleration Probe spins like a slow lighthouse, about 4 revolutions each minute, and with every turn it paints a thin ring upon the sky. Day by day, the spin axis is nudged by about 1 degree, so the rings knit together into a full map of the heavens. In this way, the observatory can complete a global portrait roughly every half year. Because its instruments have far greater collecting power than their predecessors, the same coast can also be watched in quicker strokes. The low and mid-energy atom cameras can resolve genuine changes on the scale of a season. The highest energy camera can catch week-by-week shifts. Layer that cadence over the spinning and you have not a snapshot but a meteorologist's chart. Contours of pressure and flow across the heliosphere refreshed in a rhythm human beings can live by. Those layers begin with the energy of the messengers, the most delicate imager, IMAP-Low listens to neutral atoms at the soft end of the spectrum, the energies where the outer heliosphere's slow breath dominates. IMAP-High, in two identical heads, canted at different angles to the spin axis, adds the middle register disentangling species and sharpening the map. And then IMAP Ultra 2 Eyes again extends the melody up to hundreds of kilo-electron volts, where the boundary's briskest motions sing. All three sweep the sky as the spacecraft turns rings, becoming bands, bands becoming hemispheres, until after about 6 months we hold a complete atlas. Crucially, IMAP's vantage beyond Earth's magnetic skirts and its much larger collecting power mean cleaner, surer lines than before. The result is a set of energy isobars that can be stacked and compared: soft tones for slow structure, bright tones for fast. But even a map has memory, and in this frontier the memory is written in transit time. A change that begins at the sun, say a broad pressure surge tied to a coronal mass ejection, must first travel the long road to the termination shock, and then into the heliosheath. That alone can take on the order of a year. At the frontier, charged particles exchange electrons with neutral atoms and become straight-flying neutrals, which then race home to 1 astronomical unit. Their flight time depends on their energy. A 1 kilo-electron-volt hydrogen neutral needs a little over a year to cross roughly 100 astronomical units. 10 kilo-electron-volts can return in a handful of months. The gentlest energies can take many years. The consequence is simple and profound. The ribbon and the globally distributed glow do not all answer at once. The high-energy maps twitch first, then the middle, and only later the low. The frontier's weather is therefore a harmony with built-in delays, precious predictable delays that the new observatory is designed to measure. We know this is the right way to think because we have already heard the echo at the gate. For decades, the Voyager plasma wave antennas have picked up radio tones that arrive after great pressure fronts have rolled through the heliosphere. One classic analysis, now a kind of folkloric page in heliophysics, tied interplanetary shocks to radio emissions with a travel time of roughly 400 days. Just the sort of timescale you would expect for a surge sent from the sun to the heliopause. That is the language of a coastline. With memory, a storm rings the bell many months later, and the tone can be read for distance and density. IMAP's layered neutral atom chronicle turns that episodic bell into a continuous stave, so that week by week, season by season, we will see the frontier swell and relax. Add to this the simple poetry of ultraviolet light. The glow's photometer does not make pictures. It counts photons at the exact color of hydrogen's lime and alpha line as the craft turns. Each click is a scattered solar photon re-emitted by interstellar hydrogen drifting through our system. String the clicks together over a spin, a day, a month, and you have a drift chart for the river of hydrogen itself, thicker here, thinner there, breathing with the solar cycle. Because GLOWS rides the same platform as the neutral atom cameras, its rainfall of photons can be read alongside the energy maps, a clean, co-registered ledger of gas and pressure and field. And the calendar is not kept by IMAP alone. Riding the same ascent, the Space Weather Follow-On Observatory from the National Oceanic and Atmospheric Administration is now on its way to that first balancing point. It will begin round-the-clock service after commissioning, measuring the solar wind's plasma and magnetic field, and imaging the sun's great ejections. Its stream is the now against which IMAPs later can be tuned when a pressure surge leaves the solar corona. We mark the date. When the mid and high energy neutrals brighten months after we tie the peaks together and learn the road's length. When the low energy maps answer years hence, we confirm the shoreline's deeper memory. The Carruthers Geocorona Observatory completes the triad by watching Earth's enormous hydrogen crown in ultraviolet, a local lantern to remind us what every signal must cross on its way out and home again. 3 clocks, 1 tide table. If you are planning journeys, this kind of calendar answers a quieter human question: when is the sea kindest? The rule of thumb, hard won and still being refined, is that the cosmic ray rain is weakest near the crest of the sun's 11-year rhythm. The heliosphere's magnetic weave tightens then, and the galactic particles are turned away more effectively, lowering the deep space background dose. There are caveats. The sun also throws more storms in its active years, and those solar energetic particle events can be sharp and dangerous. But if you are thinking about long voyages, most studies point to the seasons around solar maximum as the gentler windows for the slow, cumulative rain of galactic cosmic rays. What IMAP adds is the ability to forecast those windows with cartographers' precision by tying the neutral atom maps, the ultraviolet glow, and the solar wind log into a single almanac. There is even a short-term rhythm to learn the spacefarer's equivalent of low and high pressure passing over a coastline. When the sun launches a large ejection, the magnetic foam sweeps away a fraction of the galactic cosmic rays, causing a brief global dip in their counts. A four-bush decrease felt in detectors from Earth's surface to Mars and beyond. With the space weather follow-on, watching the ejection leave and IMAP recording how the boundary brightens months later, in certain energies we can begin to predict not only that a dip will arrive, but how long the frontier will wear its imprint. Over time, the mission's 3-month and 1-week responsiveness at different energies will let us learn which parts of the ribbon and the globally distributed glow echo which kinds of storms and after how long. That is how a shoreline becomes a timetable. So we have in our hands a new sort of calendar rings of atoms laid down by a spinning lighthouse, seasons of ultraviolet rain, a logbook of the wind leaving home, and out beyond the surf, a steady hum that tells us when the sea thickens. In the next part, let us follow a single pulse all the way through, watch it blossom in a coronagraph, feel it gust past the first Lagrange point, see it brighten the ribbon at high energy within a season, and at lower energies a year or two later, and hear at last the Voyager note rise as the swell rolls by. That journey taken slowly shows exactly how we turn images into dates and dates into safe passage. Let us follow a single pulse born on the sun, all the way to the edge of home and back again in messengers of light and atoms. Imagine a coronal mass ejection lifting from the sun's bright limb, an expanding bubble of magnetized plasma. Near the first Sun-Earth balance point, the Space Weather Follow-On Observatory watches the eruption with its coronagraph and samples the solar wind and magnetic field in real time. To forecast as those streams are the first entry in the logbook that will let us time the echo at the frontier months later. Downstream, the pulse does not simply fade. Merged interaction regions, the great shells built as faster wind catches, slower plough outward and survive the long road to the heliopause. Models and observations of the extraordinary storms of early 2012 showed just this. A cluster of shocks at Earth combines into a single deep space front predicted to reach roughly 120 astronomical units in about 1 year, and heard out there as a burst of low-frequency radio emission. In later years, as Voyager 1 drifted in the interstellar medium, similar tsunami compressions were sensed again as they pressed on the boundary and rang the plasma like a bell. These are the most exquisite timestamps. A storm leaves the sun, and about a year later the coastline sings. How do we see that echo in pictures? This is where the energetic neutral atoms arrive, the straight-flying couriers of the frontier. When fast ions at the heliopause steal electrons from neutral atoms, they become neutrals themselves and race homeward unbent by magnetic fields. Their flight time, like the return of sound across a valley, depends on energy. A 1 kilo electron volt hydrogen neutral needs a little over 1 year to cross a characteristic heliospheric distance of 100 astronomical units. Higher energy neutrals come sooner, lower energy later. In other words, the shoreline answers in harmony. High energies brighten first, middle energies after a season or two, the softest notes only after years. IMAP turns that harmony into a calendar. The observatory is a simple sun-pointed spinner, turning about 4 revolutions each minute, so its instruments sweep the sky in nested rings. With far greater sensitivity than its predecessor, it can build global maps about twice each year and partial maps within a season, stacking energy bands like isobars on a weather chart, IMAP low for the softest neutrals, IMAP high. Across the middle, an IMAP ultra for the brisk high energy notes. The cadence is the point, week to week at the top end, season to season in the middle, and half-year to multi-year at the low end, so that a single pulse from the sun writes itself over time across the whole atlas. There is a second quieter clock on the same deck. The tiny instrument called Global Solar Wind Structure glows, does not make images. It counts photons at hydrogen's Lyman alpha wavelength as the spacecraft spins. About 1,000 photons per second patter into its detector. A soft rainfall that maps the helioglow, the ultraviolet shimmer made when interstellar hydrogen drifts through our system and re-emits sunlight. Read alongside the neutral atom layers. That rainfall tells us how the interstellar river is threading the inner system just now, and how the sun's long rhythm is stroking it. Let us trace the pulse then as a mariner might. Day 1, the coronagraph on the operational sentinel at the first Lagrange point flags a liftoff. The in situ instruments there record the speed and magnetic field of the front as it sweeps past. Sometime in the following months, depending on the wind's temperament and the way the fronts merge, that pressure surge reaches the termination shock and begins to rework the heliosheath. In the high-energy neutral maps, a subtle brightening appears first, a tightening of the fabric at certain longitudes. Weeks to a handful of months later, the mid-energy bands answer, and after about a year, the softest energies show their slow rise. This ordering is not artistic license. It flows from the energy-dependent travel times of the neutrals and from the road length to the frontier. Beyond the gate, the old traveller keeps time. Voyager's plasma wave antenna hears a persistent narrow hum in the very local interstellar medium. It is a quiet chorus, steady, almost monotone, that tracks the electron density outside our bubble. When one of these great merged fronts disturbs the boundary, the pitch rises as the interstellar plasma is gently compressed, a change heard many months after the eruption itself. When you place those notes beneath IMAP's layered portraits, the geometry of the shoreline resolves inside breath, outer ring, and the mid-distance sketched by the neutrals. Even the ribbon, the elegant arc first drawn by the interstellar boundary explorer, becomes a timing mark. The ribbon is brightest where our lines of sight are perpendicular to the local interstellar magnetic field, a sign that the galaxy's field is cinching our tent. Because the ribbon's glow is made of those same neutral couriers, its different energy slices respond with the very delays that make the frontier readable. We expect the upper slices to twitch first after a strong pulse, and the gentler ones to carry the afterimage into the next year. With IMAP's finer energy steps, we can watch that progression cleanly. Spin, cadence and delay together give us a practical ephemeris. IMAP's spin of roughly 4 revolutions per minute builds rings into hemispheres. Its sensitivity yields half-year global maps and seasonal partial map. Its energy coverage from a few thousandths to a few hundred kilo-electron volts sets the time of flight ladder that turns a solar event into a measured, layered response at the edge of home. Read beside the operational sentinels now, and the Voyager's distant hum those layers. Let us say not only that a front has left, but when and where the tent will tighten. There is a gentle satisfaction in how the instruments rhyme. The operational sentinel watches the sun lift a hand. Months later, IMAP's high-energy canvases catch the first tightening of the wall. A season later, the middle registers answer. After about a year, the low-energy glow brightens, and beyond the boundary, the Voyager hears the interstellar plasma shift its tone. Science becomes weather, and weather becomes a calendar a crew can live by. In the next part, I want to fold that calendar back into daily life, aboard how you turn an eruption's timeline into a week of work lists, how a water-walled storm closet and a rescheduled spacewalk become in practice the art of a kinder passage, and then lift our eyes again to the wider lesson. What these delayed echoes teach us about the shape of the heliosphere itself and the subtle ways the galaxy's magnetic field writes its hand upon our shore. So take that eruption's timeline and fold it into the life of a ship. The pulse lifts off the sun. The operational sentinel at the first Lagrange point, Noah's Space Weather Follow-on Observatory, catches the rise in white light images and samples the wind and the magnetic field in real time. That stream is your now. It is the log entry that starts the echo clock you will read months later at the border. On board, the week writes itself with a kind of tender precision. Day 1, you see the front depart in the coronagraph and feel the field turn at the century. You shuffle the plan, heavy work that can wait moves to another orbit. Delicate instrument runs slide into the lee of the storm. Deep space weather is not an abstraction, it is what a checklist sounds like. Noah's observatory exists to make that sound daily and reliable, a full-time watcher that turns solar mood into practical time-stamped warnings. Then we practice what mariners have always practiced. We sail by echo. A merged interaction region, those broad shells raised as faster wind overhauls. Slower wind can cross the planetary orbits with its identity intact, push through the termination shock and press on the heliosheath. In earlier cycles, great tsunami compressions launched from the sun were sensed a long year later at the frontier, their passage registering as radio-loud disturbances and density changes a bell that rang from the coast. Voyager's team has described a sequence of such waves in interstellar space. No poetry was required to name them. IMAP takes that echo and turns it into a calendar. Because energetic neutral atoms fly straight and carry the memory of where and how fast they were born, the high-energy maps answer first, then the middle energies, and only later the softest notes. Over weeks, you see the briskest bands tighten in certain longitudes. Over seasons, the middle registers brighten. After a year or more, the low-energy canvases complete the reply. That ladder of response is not guesswork, it is built into the physics of charge exchange and time of flight, and IMAP's 3 images were designed to resolve it. You read that ladder alongside a quieter clock. Since the year 2017, one of the Voyagers has been hearing a persistent narrow plasma tone in the very local interstellar medium. Treat pitch as density, and you have a steadily sampled barometer of the sea outside. a slow, graceful undulation in electron density beyond our wall. When a deep pressure surge rolls out from the sun and reaches the gate that hum rises, we now have density outside wind and field inside, and IMAP's layered portraits between the triangulation every navigator wants. All of this folds down into a human rhythm. A crew wakes to three voices: Noah's sentinel with the day's wind and field and any fronts on the move, IMAP's latest partial rings layered by energy like isobars on a weather chart, and the distant voyagers hum ticking away the state of the outer sea. If the high-energy atoms have begun to tighten in a certain quadrant, you treat that sector of the sky as the windward rail. If the hum outside rises a few months later, you nod and mark the bell the coast has rung. There is a kind of confidence that comes when maps rhyme with music. At the practical level, the ritual becomes domestic. Water bags migrate to thicken one wall of the storm closet. A spacewalk drifts by a day because prudence is just patience wearing a tool belt. If the front promises a four-bush hush, those characteristic global dips in the galactic drizzle that follow a passing shock you pencil-sensitive detector work into the lull with the caveat that squalls are quirkish and shelter must be near to hand. The point of the calendar is not heroics, it is kindness. And yet quietly, this same choreography teaches us about the shape of home. When the high-energy maps twitch first in lanes roughly perpendicular to the field beyond, and when the bright arc we call the ribbon swells in concert, we are watching the galaxy's magnetic hand cinch the walls of our tent. Ibex first revealed that ribbon, an elegant swath of energetic neutral atom light aligned with the external field, and years of mapping showed it breathe with the cycle. IMAP's finer energy steps and broader dynamic range mean we can now time that breathing with exquisite care and separate how much of the painting is done by secondary neutrals just beyond the heliopause versus other subtler choreographies. The ribbon is both compass and tide table. The echoes also test geometry. For decades, we sketched a long comet's tail. Modern models that honor magnetic tension and the pressure of pickup ions suggest a more compact, croissant-like figure whose twin jets fold back under a firm field. If a single pulse tightens one lobe first at high energies and delays the reply in the opposite quadrant, the timing and pattern offer evidence for that pinch, or for a broader wave-softened nose rather than a hard bow shock. The absence of a roaring shock ahead, long argued from combined models and confirmed by years of frontier imaging, tells us the sun negotiates with its cloud rather than battering it. Watching where and how quickly the neutral layers answer is a way to weigh that negotiation. Zoom back to the neighborhood and the atlas becomes richer still. Far from the glare, New Horizons mapped the diffuse Lyman alpha glow over almost the whole sky and found it brighter and smoother than many of us expected, consistent with light from young hot stars washing the walls of the local bubble, and then being resonantly scattered into our eyes. Fold those ultraviolet maps into IMAP's helioglow counts from near Earth, and the ribbon's energy-layered tide, and you begin to connect room and coast the luminous cavity around us, the hydrogen wall at our edge, and the pressure that tightens our shelter today. In that sense, the cruise week is a microcosm of a civilization's learning. We have a watcher for the sun's moods, a cartographer for the frontier, and a distant ear in the outer dark. Tie them together, and you can choose quieter months for long crossings, plan work around the hushes that follow fronts, and read the wider sea in the pattern of a single luminous arc. This is what it means to understand the shore before you cross to interstellar space, to let the physics become a calendar, the calendar a habit, and the habit a gentler way of traveling. In the next part, I want to widen the circle one more step beyond navigation to meaning and follow, how this living shoreline reshapes our ideas of habitability and time, how cosmic ray seasons braid with climates and atmospheres, how other stars' ribbons and hydrogen walls will read to us when we learn to see them, and why in the quiet between storms the sun's great bubble lets a small civilization look outward and feel at home. Lift the idea of shelter into the language of life. When I speak of the heliosphere as a tent, I mean a real modulation of what reaches our skies and our skin, a softening of the high-energy rain from the galaxy, and a reshaping of the solar storms that sweep past. The voyagers taught us that beyond the boundary, the interstellar plasma hums at a steady pitch, a few hundredths of an electron per cubic centimetre, and that this hush rises and falls as distant pressure fronts pass. It is as if the ocean beyond our bay swells on a long tide. Inside the water sloshes in sympathy. That is the foundation upon which the rest of the human story is built. On longer rhythms, the sun itself conducts the orchestra, When the solar magnetic field is wound tight and the wind is muscular, the galactic drizzle slackens. In quieter years, it grows stronger. We have drawn that anti-correlation for decades in the patient scribble of neutron monitors and spacecraft counters, and in the delayed echoes that ring the frontier after great pressure surges leave the corona. One classic lesson is that merged interaction regions, broad shells, where fast wind overtakes slow, can take about a year to reach the heliopause, and their arrival is heard as a radio loud disturbance. The coastline has a memory, and the time it takes to answer is a scale on our calendar. What does that mean for air clouds and the breath of worlds? The connection between galactic cosmic rays and clouds has been tested with unusual care. At the European Laboratory near Geneva, an experiment called Cloud Cosmics, leaving outdoor droplets, built a controllable slice of atmosphere to see how ionization seeds aerosols. The results are nuanced. Ions from cosmic rays can indeed help form the tiniest clusters, and in cleaner pre-industrial air they likely mattered more. But across the modest swings of the solar cycle today, the influence on clouds and climate appears limited. It is a lovely reminder that influence is not control, and that the heliosphere's gift to habitability may be gentler and more indirect than once imagined. Solar storms are a different animal, local weather rather than climate. When the sun hurls a storm rich in energetic protons, the high atmosphere's chemistry can be bruised. Models suggest that a Carrington-class event, the 19th century outburst that lit telegraph wires, would carve temporary bowls in ozone at high latitudes and spike odd nitrogen compounds through the stratosphere. In the long archives of ice, researchers have even traced brief nitrate surges that some attribute to solar proton events, proxies still debated, but evocative of a sky that records the sun's temper. This is the scale at which a calendar of the heliosphere begins to matter. To us, not grand ice ages, but months of altered exposure, days of caution for crews, and a slow reshaping of upper air chemistry after the largest blows. And then there is the quiet arithmetic of dose. On Earth, the magnetosphere and the sky together reduce the cosmic rain to a background drizzle. Aloft at flight altitudes, the drizzle thickens with latitude and solar state. On the Moon and Mars, where global magnetic shelter is absent or faded, instruments have measured daily dose equivalents that remind us how naked a surface can be without a strong tent. Those numbers rising towards solar minimum and softening near the crest of activity translate directly into planning for exploration and habitation. They also whisper a deeper truth. The heliosphere's long breathing is not academic. It is the tempo of safe work beyond our air. Look outward and the lesson widens. Other suns blow other winds, they draw other tents. We cannot weigh those winds directly in most cases, so astronomers learn to read a fainter sign, a tiny extra bite in the hydrogen Lyman alpha line of nearby stars. That atmospheric absorption is cast by a hydrogen wall, where a star's wind meets the interstellar medium, and it has become a primary tool for estimating mass loss from cool sun-like stars, by extension the reach of their shelters. It is delicate work refined over decades by careful modelling and by comparisons with other tracers, but the implication is clear. Worlds inherit part of their safety not just from their own fields and skies, but from the health and geometry of the larger bubble their star inflates. Around the small red suns, dwarfs that hold most of the galaxy's rocky planets, the stakes are higher. Habitable zones huddle close to the furnace. Winds are stronger, flares and perhaps mass ejections more common. Models for our nearest neighbour, the planet circling Proxima Centauri, suggest dynamic wind pressures, thousands of Earth equivalents, and magnetopauses that pulse within a planetary radius or two. Add intense ultraviolet and X-ray light, and you have an environment where atmospheres work hard to endure. We can soften the picture with oceans with strong planetary fields, with chemistry resilient to stress, but the baseline remains some neighbourhoods are noisier, and yet there is a consoling symmetry here. The very techniques we use to read our own frontier are the ones we will carry outward. The Interstellar Mapping and Acceleration Probe, near the first Lagrange point, is not only a heliophysics mission, it is a template factory. By separating the contributions of hot pickup ions, cooler solar wind ions, and the firm hand of the magnetic field beyond, by watching the famous ribbon brighten where our lines of sight lie sideways to that field, the mission tells us which ingredients matter and why. That recipe travels. When we weigh another star's wind by its hydrogen wall, when we ask whether an exoplanet's aurora might be crushed close to its surface, we are leaning on the same grammar. Even our neighbourhood's architecture turns out to touch habitability. The sun sails inside the local bubble, a cavern carved by ancient supernovae. Its expanding shell corrals the gas that births young stars, and the pressure inside leans upon our own tent. Recent three-dimensional reconstructions show that many nearby nurseries lie on that bubble's surface and are moving outward together, an elegant choreography connecting explosions long past to star-forming clouds today and to the soft push felt by the heliosphere now. It is humbling to think that life here has always been lived inside the breath of a superbubble. So habitability becomes a braid of shelters, the planetary magnet and sky, the stellar bubble that filters the galaxy, and the larger room of the local bubble that sets today's pressure and field. In that braid, cosmic ray seasons do not decree climate, but they do colour the radiation weather in which we explore. Solar storms do not change the world, but they leave brief chemical fingerprints on the high air and remind us to keep a storm closet close. And as we look outward to other suns, a tiny bite in a stellar line can tell us whether a world lives under a stout tent or in a thin-walled lean-to. In the next part, I want to bring this all the way home to tie the ribbon, the hydrogen wall, and the patient hum beyond the gate into a single humane almanac. We will ask what interstellar mapping and acceleration probes' first full-sky portraits can teach us about the safest months for outward travel, how a civilization might schedule its great departures upon the sun's long tide, and why. Before we cross to interstellar space, understanding the shore is an act of care. So let's finally bind the poetry to a timetable, a humane almanac you could pin above a ship's galley table. Since late September of the year 2025, the Interstellar Mapping and Acceleration Probe has been coasting to the first Sun-Earth balancing point, where it spins like a slow lighthouse and begins to turn, returning neutral atoms into weather charts for the edge of home. It lifted off aboard a Falcon 9 from Launch Complex 39A with two companions, the National Oceanic and Atmospheric Administration's Space Weather Follow-on Observatory for real-time solar weather and NASA's Carruthers Geocorona Observatory to watch Earth's immense hydrogen halo. 3 eyes, 1 promise, shore as weather, weather as calendar. The cadence matters because a civilization's departures happen on calendars, not on blind faith. IMAP's cabinet of 10 instruments is arranged to read the frontier in layers: IMAP low for the softest energetic neutrals, IMAP high for the middle register, and IMAP ultra for the brisk high energy couriers, a magnetometer to hear the field, spectrometers to weigh solar, wind ions and pickup ions, and a tiny photometer called GLOWS to count hydrogen's Lyman alpha photons, the helioglow clicking like gentle rain as the spacecraft turns. The result is less a picture than an atlas, with depth high energies answer first to a disturbance. Middle energies respond with a seasonal lag, and the softest notes take a year or more to arrive. That built-in delay is not an inconvenience, it is the scale on our cosmic barometer. To know what to expect, you listen to the far side of the gate. One of the old voyagers has been hearing a narrow, persistent hum in the interstellar plasma, a steady tone whose pitch reveals the electron density beyond the heliopause. The beauty of that discovery is its continuity. The tone undulates gently over years, and it rises when great pressure pulses launched at the sun finally reach the boundary. Inside breath, outside reply music you can steer by. And now the rule that has held for generations, written anew in fresh data, the grand anti-correlation. When the sun is busy, magnetic field wound tight, wind vigorous, the galactic drizzle thins. When the sun is quiet, the drizzle brightens. Long baselines from neutron monitors and space instruments reinforce the pattern, while modern analyses continue to show strong negative correlations between cosmic ray counts and solar activity. It is this slow breathing that a departure window must respect. On quicker timescales, you pencil in the hushes. A coronal mass ejection can sweep a magnetized sheath through the inner system, and for a few days deflect the galactic rain a Forbush decrease. It is the only weather I know that announces both hazard and a small kindness risk from the storm's own particles, but a temporary easing of the background drizzle. The physics is well rehearsed in the literature. Our new Sentinel will now flag the front at liftoff, while IMAP times the echo months later when high-energy neutral maps tighten first and lower energies follow with their graceful delay. The third hand on the wall clock is ultraviolet. GLOWS is a single-pixel Lyman alpha photometer, beautifully simple, a photon counter that rides with the atom cameras. So as IMAP spins, it logs the faint helioglow drawn by interstellar hydrogen drifting through our system. Read its counts alongside the atom maps and you get gas pressure and field in one ledger. The instrument's design notes read like a love letter to clarity, a baffled collimator, a spectral filter, a channel electron multiplier, counting each photon as a click, a daily sky that tells you how the solar wind structure shifts with the 11-year rhythm. Carruthers completes the near-Earth context. It stares back at our own world to image the geocorona, the vast hydrogen halo that every outbound signal and spacecraft must cross, and to watch how that crown swells with seasons and storms. For operations, it is more than pretty. Communications, drag and background all live in that glow. It is part of the local weather a ship must traverse before the deep sea. Now fold those strands into an almanac you could actually use. First, choose your era. The gentlest seasons for the slow, cumulative galactic drizzle cluster around solar maximum when the heliosphere's magnetic weave is tautest. You accept more frequent squalls, but your baseline is kinder. As the cycle wanes, the drizzle rises, even as the storms ease. That is the long tide upon which to schedule great departures. Second, watch the fronts. When the space weather follow-on coronagraph shows a broad liftoff and its in-situ monitors confirm a strong magnetic sheath, you mark the day, because in roughly a year, if the pulse survives to the boundary, the frontier will likely brighten in high-energy neutrals, and later the interstellar tone will rise. That echo writes a date on the ribbon. Third, read the ribbon itself. The luminous arc of energetic neutrals hangs where our sightlines lie perpendicular to the local interstellar magnetic field. IMAP's finer energy steps will watch it breathe. Upper bands twitch first, after a strong pulse, lower bands lag into the following year. When that arc swells, the galaxy's hand is cinching our walls and we thread our lanes accordingly. Fourth, keep a finger on the ultraviolet rain. If GLOW shows shifts in the helioglow distribution and Carruthers sees the geocorona flare, you are feeling the environment your craft inhabits today. It is a local tide table to lay beside the global maps. Fifth, hold the far-field hum in one ear. When Voyager's tone climbs, the outer sea has thickened. When it falls, the pressure has eased. You are listening to the other side of your shelter. There is one more grace note. Far past the giant's New Horizons has sketched the Lyman Alpha sky from the deep, an unexpectedly bright, smooth, ultraviolet dusk, likely lit by hot young stars, shining on the inner walls of the local bubble. That diffuse glow is the room your tent sits in, and it helps separate which parts of the ultraviolet sky are the neighborhood and which parts are the edge of home. Fold it into the almanac, and the coastline gains context. What emerges is not a single go or no-go, but a way of living with a moving magnetic sea. The long tide of the 11-year rhythm sets the era, the fronts and hushes set the week, the ribbon's energy, layered breathing sets the lanes, the ultraviolet rain and geocorona set your local air, and the distant hum sets your expectations for the months to come. With those dials aligned, a departure stops being an act of bravado and becomes an act of care. And if you ask what that care is for, beyond engineering, I would say it is for the people who will make the crossing. A storm closet lined with water, a spacewalk slid by a day, a launch penciled toward the cycle's crest. These are quiet kindnesses born of an atlas. In the next part, I want to take that kindness and walk it to its limit, to imagine the first decades in which we live routinely beyond Earth's magnetosphere. How habitats breathe with the sun, how detectors learn to rest on the hush of Forbush dips, and how a civilization sets its own great departures upon the slow tide of a star. Imagine the first decades in which we live routinely beyond Earth's magnetic cradle. I picture mornings that begin with the same quiet ritual, a glance at the upstream sentries, a listen for the long hum beyond the gate, and then the day's work shaped to the sky. Since late September 2025 Interstellar Mapping and Acceleration Probe, IMAP has been our cartographer, stacking energetic neutral atom maps in low, mid and ultra-high energy bands, while the tiny GLOWS photometer counts the faint heartbeat of hydrogen's Lyman alpha glow. Those instruments are simple in idea and exquisite in execution. Neutral atom cameras to trace the pressure at the heliosphere's edge, and a single pixel ultraviolet ear to hear how interstellar hydrogen is threading through our system today. We're not watching in isolation. NOAA's Space Weather Follow-on Observatory at Lagrange, one riding to space with IMAP, keeps the now for forecasters a compact coronagraph to see liftoffs and in-situ plasma and magnetic field sensors to sample the wind that will arrive at our hull in tens of minutes to hours. On the same ascent, NASA's Carruthers Geocorona Observatory joined the perch to map Earth's vast hydrogen halo, the geocorona, so even the tenuous air we first cross is part of the picture. Together, those three make shore into weather you can actually plan around. The day-to-day choreography becomes domestic. On a lunar outpost with no global magnet, we know the ambient drizzle in our bones. The Chang-4 dosimeter measured an average surface dose on the order of 1 and a bit millisieverts per day, roughly 60 microsieverts per hour, numbers that breathe with the solar cycle, and set the background rhythm for work and rest. On Mars, Curiosity's RAD instrument reports a typical surface dose near 2/3 of a millisievert per day under quiet skies, with the cruise through deep space closer to twice that. Those are not abstractions, they're the weather of the body. Against that steady rain, we learn to use the sky's hushes. When a coronal mass ejection throws a magnetized sheath across the inner system, detectors from Earth to Mars often register a forbush decrease, a brief dimming of galactic cosmic rays that last days. On the Martian surface, RAD sees them. In orbit, MAVEN does too. They're warning buoys. Of course, the storm itself can be dangerous, but for astronomers and crews, they're also small gifts. Windows to run the most sensitive instruments, or to venture briefly when the deep background softens. The longer tide still sets the era. When the sun is active, magnetic field wound tight, wind vigorous, the galactic drizzle thins. In quiet years, it climbs. We've drawn that anti-correlation across many cycles with neutron monitors and spaceborne counters, and we can now see its echoes in the frontier itself, as IMAP's high-energy maps twitch first and lower-energy maps answer months later. That's how a civilization schedules departures, bias the great crossings towards solar maximum to trim the cumulative galactic dose and harden plans for the squalls that come with a busy star. There is a comfort in having a second hand on the wall clock far beyond the heliopause. Voyager's plasma wave antenna adrift in interstellar space hears a persistent narrowband chorus whose pitch converts to electron density just outside our bubble. It is to me the softest barometer ever built. When great pressure pulses roll outward, that tone climbs months later, proof that the inside and the outside remain in conversation. Reading that hum beside IMAP's layered portraits and the Space Weather Sentinel's coronagraph turns physics into a calendar you can live by. In practice, the habitats of those decades will breathe with that calendar. You'll see water bags migrate to thicken one wall when the upstream field turns unfavorable. A spacewalk will slide by a day because prudence is just patience wearing a tool belt. You'll pencil the quietest detector runs into the lulls that follow shocks, with a storm closet lined in low-Z materials always near to hand. The art is not heroism. It is kindness engineered into furniture and timetables. And because IMAP's maps are layered by energy, they don't just show where the coastline brightens, they help us tell how deep the pressure ridge is, so a crew can decide whether to hunker down for hours, days, or longer. The wider room matters too. From nearly 57 astronomical units, New Horizons used its ALICE spectrograph in September 2023 to sweep the Lyman Alpha sky and found a bright, surprisingly uniform ultraviolet dust consistent with hot young stars lighting the inner walls of our local bubble and resonant scattering amplifying the glow. That backdrop reminds us that the hydrogen wall at our own boundary is not the only painter of the ultraviolet sky. There is a room around the tent, and it glows. When GLOWS near-Earth counts drift in the same direction, we're watching neighborhood and shore together. None of this is abstract to the people who will make the crossings. A ship's morning might begin like this. SWFO's stream shows a broad liftoff with a strong field, so operations tighten timelines and restack consumables around the shelter. IMAP's latest high-energy tiles show a subtle brightening in one quadrant, an early tightening at the frontier that will ripple down energy over the coming seasons. Carruthers images of the geocorona, meanwhile, say the local halo is calm, good for comms and background. And in the far dark, the old Voyager's tone is steady. A week writes itself from those 4 lines. I find it quietly beautiful that our first sustained life beyond the magnetosphere depends on instruments that count one thing at a time. A neutral atom, a single ultraviolet photon, a tiny voltage on a wire as a plasma wave passes. Out of such clicks, we are learning to be gentle travelers. We are, in a real sense, letting the heliosphere remain a home, even as we learn to leave it, treating it not as wallpaper, but as weather with seasons and tide tables and local rips you can see from the bridge. In the next part, I want to knit that human calendar back to the grander geometry, how the ribbon's slow breathing fixes the direction of the magnetic field, beyond how the croissant-shaped heliosphere flexes with the cycle, and how IMAP's energy-layered echoes will let us prove the shape of our sun's bubble while we sail inside it. So from that human calendar back out to the grand geometry, the sky itself gives us a compass painted not in starlight, but in neutral atoms. Years ago, a small pathfinder, interstellar boundary explorer, drew a narrow, luminous arc across the heavens. a ribbon brightest exactly where our line of sight lies sideways to the magnetic field outside the heliosphere. That geometry is the key, because the ribbon tracks sight lines perpendicular to the external field, its center and curvature. Let us infer both the direction and even the strength of that field as it drapes around our bubble. Analysis of the ribbon's shape and energy dependence have pinned the local interstellar field to a few microgauss and fixed its direction with exquisite precision. In other words, a glow at the edge of home doubles as a compass rows for the galaxy's breeze. It is a quiet marvel that the ribbon breathes with our star. Over more than one solar cycle, IBEX maps showed the arc brightening and fading, with a delay and echo of the sun's changing wind and field written into the boundary. When the wind thickens and the field tightens, pressure piles into the heliosheath. Months and years later, that shove reappears in increased neutral atom flux at particular energies and longitudes. With an entire cycle now charted, the lesson is clear. The heliosphere flexes as the sun does, and the ribbon is its tide mark, rising and falling in time with the star's long rhythm. That long rhythm is what the new cartographer, interstellar mapping and acceleration probe was designed to resolve. IMAP launched on Wednesday, the 24th of September, 2025, atop a Falcon 9 from Launch Complex 39, bound for the first Sun-Earth Lagrange point. From that lighthouse perch, it spins and gathers energetic neutral atoms across three bands, low, high and ultra, so that the frontier can be rendered in layers of energy. Alongside ride companions with complementary roles, NOAA's Space Weather Follow-On for real-time solar wind and magnetism, and NASA's Carruthers Geocorona Observatory to map Earth's vast hydrogen halo. 3 missions, 1 choreography, near-term weather, the far frontier, and the local veil, all on the same page. What those layers buy us is depth. High-energy neutrals speed home first, mid-energy arrive with a seasonal lag, the softest energies take a year or more. That ladder of return times turns the ribbon's breathing into a timed echo. When a broad pressure pulse leaves the sun, spotted immediately by the operational Sentinel's coronagraph and plasma monitors, we can watch for the ribbon to twitch first in the upper bands, then in the middle, and finally in the low. The delays are the proof. They measure the road to the heliopause and back, and they discriminate swift outer sheath tightening from slower, deeper reworking of the boundary. It is particle seismology for the shore. The geometry we are testing with those echoes is no longer the old schoolroom comet tail. Models that honor magnetic tension and the muscle of pickup ions suggest a compact, croissant-like figure, twin polar jets swept back under the grip of the field, a nose that flows into broad flanks and a tail that is braided, rather than endlessly tapering. The picture is a living one, pinching and relaxing with the cycle, and it is perfectly matched to an observatory that can watch energy by energy and season by season. The alternative myth, a roaring bow shock ahead of the sun, has given way to a gentler bow wave. Our motion through the local cloud is too measured, and the external field too firm to support a classical shock, a negotiated coast, not a battered one. And then there is the ribbon's deeper gift. It does not only point, it measures. Because the bright arc forms where the external field runs sideways to our view, detailed modeling of its circle and subtle offsets has been used to determine the field's strength and direction in our neighborhood with impressive accuracy. Just a few microgauss aimed along a line now charted in ecliptic coordinates. It is a rare pleasure in astrophysics to have a magnetic arrow drawn so legibly on the sky. With IMAP's finer energy steps and broader dynamic range, we can now follow small drifts of that arrow across the cycle and ask whether the drape of the field around our bubble itself breathes with the Sunday. There has been honest debate about how the ribbon is painted. The prevailing family of explanations emphasizes secondary neutrals ions created beyond the heliopause that are turned back and reneutralized in the very local interstellar medium, while others invoke retention regions or inhomogeneities in the gas outside. New work even explores how turbulence may mirror and guide pickup ions into just the angles that paint the arc. Here too, IMAP is decisive by splitting the glow by energy and cadence. It can test which choreography fits the timing best and how closely the arc's center remains tied to the field direction as seasons turn. If the ribbon is our compass, the continuous interstellar hum heard by Voyager 1 is our barometer. Since 2017, the plasma wave instrument has recorded a faint, narrow tone whose pitch gives the electron density just outside our wall. When merged solar wind fronts, those deep space tsunamis finally reach the gate that pitch climbs. Place those notes beneath IMAP's layered ribbon and globally distributed glow, and the shore resolves in 3 dimensions inside wind, mid-distance maps and the outer sea's density all in measured step. And then there is the room our tent sits in. From far beyond the giants, New Horizons swept the sky in hydrogen's Lyman Alpha and found a bright, surprisingly uniform ultraviolet dusk, likely the inner walls of the local bubble, lit by hot young stars, their light scattered into our view. That background gives context. The hydrogen wall at our boundary is not the only painter in the ultraviolet. The neighbourhood itself glows. With Carruthers reading Earth's own hydrogen crown from Lone and GLOWS counting helioglow near the Sun-Earth line, we can subtract room from shore and read the frontier cleanly. Put simply, the ribbon fixes the direction of the galaxy's hand, the croissant declares the way magnetism sculpts our shelter, the bow wave reminds us the negotiation is smooth, and the timed echoes in IMAP's energy layers will let us weigh rather than merely sketch the sun's bubble as it breathes. That is why I find this moment so graceful. We are sailing inside a magnetic cocoon, and yet we can prove its shape from within by listening to how it answers our star's heartbeat and how it wears the imprint of the wider field beyond. And because all good maps invite journeys, I would like to carry these instruments back to the rail of our imagined ship and show how a single season's worth of ribbon drift a rise in the interstellar hum and a change in the helioglow. Together, become a pilot's page, what lane to choose, which months to favour, and how a civilization might thread the quietest corridors through a living magnetic sea. I think of it like this. We are standing on a quiet strand at the edge of our world, and the sea that laps at our feet is made of magnetism and breath. The sun draws a shelter around us, a kind of canvas tent, stitched by fields and wind, and far away that fabric touches the wider room of the galaxy. We have spent our hour together walking that line, feeling the hem of the heliosphere between our fingers, listening for the rise and fall of distant tides. And now, as the light fades to a soft blue, I want to leave you with something simple and human, a sense that we belong to this shoreline, and that it will be here tomorrow and the day after, and deep into the seasons of our children. I can still hear the instruments in my mind murmuring like owls in the dusk. Upstream, the cartographer waits at the first balancing point between Sun and Earth, an observatory called IMAP, turning the rain of returning atoms into a living map of our border, counting patiently the faint whirls of hydrogen that drift through our neighbourhood. It is such a modest idea and such a beautiful one to sit quietly where the gravities balance and listen for messengers from the far edge of home. And beyond the gate, one of the elder craft still keeps an ear to the wider sea. VOYAGERs. Long antenna hears a narrow, persistent tone in the interstellar plasma, the thinnest of musics, a soft, steady hum whose pitch tells us how dense the ocean is just outside our wall. That hum rises and falls over months and years like the breath of someone sleeping. And in its constancy there is comfort, a reminder that even the far dark is not empty but alive and comprehensible. I like to think that this is what science does at its best. It takes the anxious questions that wake us. What lies beyond our circle of firelight? How firm is the shelter over our heads? And it answers them with small, exact kindnesses. A counted photon here, a single returning atom there, a line on a page where once there was only night. If you step back from the machinery and the acronyms, you can feel the care in it. We taught ourselves to read the sky's slow handwriting, the ribbon that glows where the galaxy's magnetic field runs sideways to our gaze, the faint ultraviolet dusk where hydrogen gathers into a ridge, the long inhalation and exhalation of our star, and we turned those signs into a calendar fit for human hands. We learned when to linger, when to venture, when to be still. There is something soothing in the scale of it. The heliosphere does not slam or rattle, it breathes. Its boundaries brighten and relax with a patience that belongs to seasons rather than seconds. The great pulses that leave the sun take months to reach the frontier. The neutral messengers that carry news back to us arrive in stages: high notes first, and then the middle, and then the low, so that even the edge of home speaks in chords. And all the while the background rain of high-energy visitors from the galaxy waxes and wanes, with the old familiar rhythm of sunspots falling gently, when the star is busy rising, when it is calm. You can live by such rhythms, you can rest by them. If you close your eyes, perhaps you can feel it. Earth turning beneath your feet, the quiet pull of the sun upon your skin, the long shelter of the magnetic tent above your head, and beyond that the wide room of the local bubble lit here and there by bright young stars. The distances are immense, but the feeling is not of distance at all. It is of belonging. We are stitched into this fabric. Our atoms were forged in older fires, and set adrift. They found one another here along this shore, under this particular tent of light. The same laws that shape a newborn star's wind shape the gentle weather that touches your cheek on a winter morning. The same field that holds a comet in its curved path holds the aurora above the poles like green silk hung to dry. The universe does not stand apart, it leans in. It is our neighbour. And so the thought I want to leave you with is a quiet one. Before we cross to interstellar space, we must understand the shore not as a limit but as a home. We do not stand on the edge of an abyss. We stand on the edge of a garden, and we are learning the names of the trees. The cartographer at the balancing point will keep turning day upon day, laying down rings of colour across the sky. The elder craft will keep listening in the dark, catching the long hum of the ocean beyond. And here beneath that shelter we will go on counting and comparing and telling one another what we have heard. In that slow conversation lies the best of us. When at last you look up, let the stars be not the cold glitter of unreachable things, but more like a choir warming up each point, a voice that will in time take its part. Let the Milky Way be not a distant river, but a path across your own fields to a friend's house. Let the sun's breath which holds us feel like the steady hand of someone you trust. The universe is vast, yes, but it is also welcoming in its way. We have learned to read its weather, we have learned to listen for its tides, and we have begun to understand that the shore is as much a promise as a place. So we draw the curtain gently. The instruments fold into their little sleeps. The graphs roll into calm. The last lines of the day's log are written. Out on the horizon, the magnetic canvas of our shelter lifts and falls with its ancient tide, and the galaxy beyond leans against it like a friendly sea. Rest in that knowledge if you can. The tent holds, the shore will be here when you wake, and the morning will bring, as it always does, the soft, patient work of understanding one photon, one atom, one heartbeat of a star at a time.